Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into a world that never knew the moon's gentle presence. A Earth spinning alone through the darkness, untouched by tides, unguided by lunar rhythms, forever strange, to us who have never lived without that pale companion overhead. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness, too. And to those who've already joined along, thank you. In the beginning, there is only absence. 4.5 billion years ago, Earth spins in solitude through the cosmic dark, its surface a molten shell of rock and metal, turning with wild abandon beneath a starlit sky. No pale disk watches from above. No gentle gravitational hand reaches down to slow the planet's frantic rotation. Here, in this alternate history written in physics and possibility, Earth completes a full day in 6 hours, sometimes less. The young planet rotates like a cosmic top, its angular momentum unchecked by any significant companion. Where our familiar world learned patience through lunar influence, this Earth knows only speed. Geological evidence suggests that early in our timeline, Earth's rotation was indeed much faster, with days lasting perhaps 6 to 8 hours. But the moon's gravitational drag gradually lengthened our days to their current 24-hour rhythm. Without this celestial break, the moonless world maintains its primordial pace. Scientists calculate that such rapid rotation would fundamentally alter atmospheric dynamics. The Coriolis effect, that invisible force that curves moving air and water, becomes extreme. Weather patterns break into narrow bands, creating a world of perpetual storms and microclimates that shift with bewildering speed. Yet, somehow, in the planet's relentless spinning, there exists a strange mathematical beauty. Each rotation carries precisely the same angular momentum it possessed at birth, like a cosmic memory that refuses to fade. The absence creates its own mysteries. How would atmospheric circulation adapt to such rapid rotation? Computer models struggle to predict the exact patterns, but they suggest intense east-west jet streams and weather systems confined to narrow latitude bands. Perhaps most puzzling of all, in a universe where angular momentum is conserved so precisely, what happened to the debris that should have formed a moon? Did it spiral into the sun? Did it scatter to the asteroid belt? The silence of space holds these questions without answers. Only 6 hours from dawn to dawn, as if the planet itself suffers from cosmic insomnia, never quite settling into the slow rhythms that might nurture complex life. But the stars above remain the same, patient and eternal, watching this restless world with something that might be called wonder, if stars could wonder. The great absence begins not with violence or catastrophe, but with simple solitude. A planet that never learned to slow down, to breathe deeply, to let time pool in tidal basins where life might one day pause to contemplate its own existence. 45 million years after the solar system's birth, in the cosmic calendar of deep time, an event fails to occur. The giant impact that should reshape Earth's destiny, the collision with a Mars-sized protoplanet that astronomers call Theia, simply never happens. In our timeline, this cataclysmic meeting of worlds launched molten rock into orbit, debris, that would cool and coalesce into the moon we know. But here, in this alternate history, Theia follows a different trajectory, perhaps swept away by Jupiter's gravity or consumed by the growing sun. The absence of this collision leaves profound consequences written in the planet's very structure. Without the giant impact to strip away Earth's early atmosphere and remelt its surface, the world retains a thicker primordial envelope of hydrogen and helium. The planet's core develops differently too, less iron-depleted than our familiar Earth, since no massive impact scattered the lighter elements into space. Geochemists studying meteorites and planetary formation models suggest that such differences would alter the magnetic field's strength and the timing of plate tectonics. Deep. Beneath the surface, the Earth's interior settles into patterns that would seem alien to us. The mantle convection that drives continental drift operates under different thermal constraints. Without the Moon's formation event to reheat and remix the planet's layers, heavy elements settle in configurations that will influence volcanism and mountain building for billions of years to come. Iron-nickel alloys pool in different proportions, creating a magnetic dynamo that pulses with its own rhythm. Yet perhaps the most poetic consequence of the missing collision lies in what remains, an unbroken chemical record of Earth's first 100 million years. Rocks from the Hadean Eon, that hellish early period, survive in greater abundance without the giant impact to erase them. These ancient stones would tell stories of the planet's youth, preserving isotopic signatures and mineral assemblages that in our timeline exist only as tantalizing fragments. Scientists could read Earth's autobiography from its very first chapters rather than beginning the story in its turbulent adolescence. The mystery deepens when considering what might have become of Theia itself. Planetary dynamics suggest that objects of its size rarely simply vanish. They must go somewhere. Perhaps it collided with Venus instead, explaining that world's retrograde rotation and hellish atmosphere. Perhaps it was ejected from the inner solar system entirely, becoming a wandering planet in the cold spaces between stars. Computer simulations offer possibilities but no certainties, leaving Theia's fate as one of the great unknowns in this moonless universe. Most intriguingly, the absence of the giant impact means Earth never experienced the wholesale atmospheric loss that such collisions cause. The planet retains more of its original volatile compounds, water, carbon dioxide, and the noble gases that provide clues to atmospheric evolution. This thicker early atmosphere might have created a stronger greenhouse effect, keeping the planet warmer despite the sun's fainter youth. The implications ripple forward through geological time like waves from an event that never happened. Only the stars witness this non-event, this cosmic road not taken. In the silence where collision should have thundered, Earth continues its lonely orbit unmarked by catastrophe, unaware of the companion it will never know. The giant impact that fails to occur becomes itself a kind of presence, an absence so profound it shapes everything that follows, like negative space in a sculptor's work that defines the form by what it does not contain. The restless planet spins beneath alien constellations, its rotation axis wobbling through space like a cosmic gyroscope slowly losing its balance. Without the Moon's gravitational anchor to steady its motion, Earth tumbles through subtle but relentless changes in orientation. What astronomers call obliquity, the angle between the planet's rotation axis and its orbital plane, varies wildly over periods of tens of thousands of years. Where our familiar world maintains a relatively stable tilt of 23.5 degrees, this moonless Earth swings between nearly upright and dramatically tilted orientations. The physics of this orbital chaos emerge from what scientists term gravitational resonances. Jupiter and Saturn, those distant giants, exert minute but persistent tugs on Earth's shape. Our planet, slightly flattened at the poles from rapid rotation, responds to these forces like a spinning coin beginning to wobble. Computer models developed by astronomers studying Mars, which experiences similar axial wandering, suggest that Earth's tilt could vary from 0 degrees to as much as 60 degrees over geological time scales. Such dramatic tilting transforms the very concept of climate zones. When Earth spins nearly upright, the The poles receive little sunlight and ice caps extend toward the equator. When the planet tilts severely, polar regions experience months of continuous summer sunshine followed by equally long winters of darkness. The tropics, normally Earth's heat engine, sometimes find themselves receiving less solar energy than the poles. Weather patterns that might have stabilized over millions of years instead undergo constant reorganization. Yet, perhaps the most beautiful consequence of this axial wandering lies in the stars themselves. From Earth's surface, the constellations appear to drift slowly across the sky over millennia, as if the heavens themselves were restless. The North Star changes regularly. Sometimes no bright star marks the celestial pole at all. Ancient civilizations, if they emerged on this world, would develop entirely different relationships with navigation and astronomy, their knowledge systems, adapted to cosmic impermanence. The geological record of such climate chaos would be extraordinary. Rock layers would preserve evidence of ice ages at the equator, tropical conditions at the poles, and rapid transitions between dramatically different climate states. Paleoclimatologists studying such strata might initially assume massive volcanic eruptions or asteroid impacts, only to gradually recognize the signature of a world whose orientation changes with astronomical precision. Most mysteriously, some scientists speculate that Earth's varying obliquity might actually stabilize over very long periods through complex feedbacks with atmospheric and oceanic circulation. The planet's ice caps, growing and shrinking with each axial shift, could alter the distribution of mass and thereby influence rotation. Like a figure skater extending and pulling in her arms, Earth might unconsciously choreograph its own dance through space. The irony emerges slowly. A world without the Moon's stabilizing influence might actually experience more regular climate changes than our own. Where our Earth undergoes seemingly random variations in ice ages and warm periods, the moonless world would cycle through predictable climate states tied to its astronomical rhythm. Yet these very predictable changes would prevent the stable conditions that complex life typically requires to evolve and flourish. Only time itself bears witness to this endless dance, this planet that cannot find its balance in the cosmic dark. Earth spins onward, tilting and straightening and tilting again, like a sleeper turning restlessly through dreams that change with the slow music of the spheres. The oceans lie motionless beneath the racing sky, their surfaces unmarked by the rhythmic rise and fall that should define coastal waters everywhere. Without the Moon's gravitational embrace, Earth's seas know only the faintest whisper of solar tides, weak forces that barely lift the water a few centimeters twice each day. Where our familiar shorelines breathe with tidal ranges that can exceed 15 meters in places like the Bay of Fundy, these moonless coasts experience changes so subtle they disappear beneath ordinary wave action. The absence of significant tides fundamentally alters the architecture of coastal zones. Rocky shores develop differently when they never experience the alternating cycles of submersion and exposure that normally create distinct intertidal habitats. Marine organisms cannot evolve the specialized adaptations for surviving periodic desiccation, the ability to seal themselves against air and sun that characterizes barnacles, mussels, and seaweeds in our world. Instead, coastal ecosystems exist in a perpetual state of shallow submersion, never quite terrestrial, never fully aquatic. Sediment transport along coastlines follows entirely different patterns without tidal currents to move sand and silt in. Predictable cycles. Estuaries, those crucial mixing zones where rivers meet the sea, lack the tidal pumping that normally drives water circulation and nutrient exchange. Freshwater from rivers tends to form distinct layers above denser salt water, creating stratified systems that resist mixing. The result is coastal waters that remain chemically isolated, their nutrients trapped in separate zones. Yet the oceanographic consequences extend far beyond the shallows. Deep ocean circulation, a global conveyor belt of currents that distributes heat, and nutrients around the planet operates under fundamentally different dynamics. While wind and temperature differences still drive major current systems, the absence of tidal mixing at continental margins reduces the vertical exchange of water masses. The deep ocean becomes more isolated from surface layers, potentially trapping nutrients and oxygen in ways that could profoundly affect marine productivity. Scientists studying tidal dynamics have discovered that even seemingly minor tidal forces contribute significantly to ocean mixing through processes called internal tides, waves that propagate through the ocean's interior layers. Without the moon to generate these internal motions, the deep ocean of a moonless world might stratify more severely, creating distinct layers that persist for centuries without mixing. Such stratification could lead to oxygen-depleted zones that expand and contract over geological time. The mystery of wave patterns in tideless seas presents its own puzzles. Waves generated by wind and weather would still crash against shores, but without the modulating influence of tides, coastal erosion might proceed more uniformly. Some beaches that owe their existence to tidal processes, where sand accumulates during certain tide stages and erodes during others, might never form at all. The familiar rhythm of rack lines marking high tide positions would be absent, leaving shores without these subtle markers of ocean behavior. Perhaps most poetically, the soundscape of these tideless coasts would lack the fundamental bass note of tidal flow. No water rushing through narrow channels, no gentle lapping as tide pools fill and empty, no rhythmic surge that matches the lunar day. The ocean's voice would speak only in the higher frequencies of wind-driven waves, missing the deep, slow breathing that gives coastal waters their familiar music. Only the wind remains to stir these stagnant seas, to provide the mixing and circulation that tides normally contribute. The ocean waits in its vast stillness, holding dissolved minerals and organic compounds in suspension, patient as a held breath that never quite learns to exhale. In the great theater of deep time, Earth's rotational axis performs an erratic ballet across the celestial sphere, its orientation changing with the slow inevitability of geological processes. Where our familiar world maintains its tilt within a narrow range thanks to the moon's steadying influence, this moonless planet experiences what astronomers term chaotic obliquity variation. Over periods of tens of thousands of years, the axis wanders across angles that would make our planet uninhabitable, sometimes spinning nearly upright like a cosmic top, other times tilted so severely that the poles point almost directly at the sun. The mathematics governing this axial chaos emerge from gravitational perturbations by Jupiter and Saturn acting on Earth's equatorial bulge. Computer simulations by planetary dynamicists reveal that without the moon's stabilizing torque, Earth's obliquity could vary between 0 and 85 degrees over timescales ranging from tens of thousands to millions of years. Mars, our neighboring world, experiences similar obliquity chaos and serves as a natural laboratory for understanding how such variations affect planetary climate. When Earth's axis tilts to extreme angles, the distribution of solar energy across latitudes becomes profoundly altered. During high obliquity periods, the poles receive more annual sunlight than the equator, reversing the fundamental temperature gradient that drives atmospheric circulation. The tropical regions, normally Earth's thermal powerhouse, experience prolonged seasons of reduced heating, while polar regions bask in months of continuous summer sunshine, followed by equally extreme winters of perpetual darkness. Such radical climate reorganization leaves distinctive signatures in the geological record. Ice core samples from a moonless Earth would reveal periods when glaciers formed at the equator while temperate conditions prevailed at the poles. Sedimentary rocks would preserve evidence of tropical vegetation at high latitudes, alternating with desert conditions, creating stratigraphic sequences that would puzzle geologists until they recognized the astronomical forcing behind these changes. The atmospheric response to changing obliquity involves complex feedbacks between ice albedo, ocean circulation, and greenhouse gas concentrations. During low obliquity periods when the planet spins nearly upright, permanent ice caps might extend from both poles toward the equator, reflecting sunlight and cooling the planet into snowball states. Conversely, high obliquity configurations could create ice-free poles and intense tropical deserts, fundamentally altering the hydrological cycle and atmospheric chemistry. Yet, perhaps the most intriguing aspect of obliquity chaos lies in its potential effects on atmospheric retention. Some planetary scientists speculate that extreme axial tilts might enhance atmospheric escape by creating temperature differentials that drive upper atmospheric winds capable of stripping away lighter gases. The interaction between obliquity variation and magnetic field strength, itself altered by the different rotation rate, could create windows of vulnerability when Earth's atmosphere becomes more susceptible to solar wind erosion. The irony of this celestial wandering becomes apparent when considering that such regular, predictable climate changes might actually be less disruptive to life than the seemingly random climate variations our own world experiences. Where Earth's ice ages arrive with complex periodicities involving multiple orbital cycles, the moonless world would experience climate changes tied directly to its axial orientation, chaotic in the mathematical sense, but following deterministic, physical laws. Most mysteriously, the planet's chaotic obliquity might eventually settle into more stable configurations through mechanisms that remain poorly understood. The growth and retreat of ice sheets change Earth's moment of inertia, potentially damping obliquity variations over geological time. Like a cosmic pendulum gradually losing energy, Earth might slowly find its gravitational balance even without the Moon's steadying hand. Only the deep patience of astronomical timescales can witness this dance. This planet that cannot find its orientation in the cosmic dark, forever tilting between extremes that would transform the very nature of seasons, climate, and habitability itself. The seasons drift across this moonless world like weather fronts that never quite settle, their patterns shifting over millennia as Earth's wandering axis redefines the very concept of climate zones. Where our familiar world experiences predictable, seasonal cycles tied to a stable 23-degree tilt, this planet knows seasons that migrate like slow-motion storms across geological time. When the axial tilt approaches 0 degrees, traditional seasons nearly disappear. Day and night become equal everywhere, and only orbital eccentricity creates mild variations in solar heating throughout the year. During these low obliquity periods, Earth experiences what climatologists might call perpetual equinox conditions. The sun rises due east and sets due west from every point on the planet's surface, its path across the sky varying little throughout the year. Temperature gradients between pole and equator become extreme, with tropical regions receiving constant, intense heating while polar areas sink into permanent twilight. Ice sheets advance from both poles simultaneously, creating a world where winter and summer lose their meaning in favor of purely latitudinal climate zones. But the planet's axial wandering ensures that such configurations never persist long enough for life to fully adapt. Over periods of 50,000 to 100,000 years, the tilt increases toward more moderate angles, and something resembling familiar seasons begins to emerge. Yet these transitional periods create their own peculiar climate states. When obliquity reaches 30 to 40 degrees, angles far more extreme than our world experiences, the polar regions swing between seasons of unprecedented contrast. At high obliquity, polar summers become furnaces of continuous daylight lasting months, while polar winters plunge into darkness so complete that carbon dioxide itself might freeze from the atmosphere. The Arctic and Antarctic transform into landscapes of impossible extremes, where summer temperatures could exceed those at the equator, yet winter cold reaches depths that make our current ice ages seem temperate by comparison. The seasonal temperature swings at high latitudes could exceed 100 degrees Celsius, differences that would shatter rocks and create unique weathering patterns unknown on our stable world. Scientists studying Mars have observed similar obliquity-driven climate, changes recorded in that planet's polar ice caps and sedimentary layers. The Martian geological record preserves evidence of ice ages that correlate directly with periods of low obliquity, while high-tilt periods created different patterns of ice accumulation and dust deposition. Earth's more massive atmosphere and extensive oceans would create even more dramatic responses to such axial variations, amplifying the climate effects through complex feedbacks between ice, water, and atmospheric circulation. The biological implications of migrating seasons extend far beyond simple temperature changes. Plant and animal life cycles, normally synchronized to predictable seasonal rhythms, would face the evolutionary challenge of adapting to seasonal patterns that change over timescales much longer than individual lifespans, but much shorter than speciation typically requires. Migration patterns, reproductive cycles, and metabolic adaptations would need to remain flexible across thousands of generations. Perhaps most poetically, the very language of seasons would evolve differently in human cultures that might arise on such a world. Words for spring, summer, autumn, and winter would carry different meanings, perhaps describing not fixed yearly cycles, but the slow drift of seasonal intensity across centuries. Calendar systems would necessarily incorporate astronomical observations of axial tilt, creating temporal frameworks based on cosmic rather than terrestrial rhythms. The mystery of how ecosystems would respond to such gradual but profound seasonal changes remains largely theoretical. Some scientists speculate that biodiversity might actually increase as different obliquity periods favor different adaptive strategies, creating evolutionary pressure for flexibility rather than specialization. Others suggest that the constant climate reorganization would prevent the stable conditions necessary for complex ecological networks to develop. Only the slow accumulation of ice and the patient weathering of stone record these wandering seasons. This planet, where climate zones migrate like tectonic plates across the surface of time itself, forever seeking stability they will never quite achieve. Deep beneath the moonless world's surface, the magnetic dynamo that should protect all life, above operates under fundamentally altered conditions. Earth's magnetic field, generated by the convective motion of molten iron in the outer core, responds directly to the planet's rotation rate. With days lasting only 6 hours instead of 24, the rapid spin creates a magnetic field geometry unlike anything our familiar world has ever known. The field lines emerge from the core twisted into complex patterns, their strength varying with the fierce Coriolis forces that govern fluid motion in the rapidly rotating interior. Geophysicists studying the relationship between planetary rotation and magnetic field generation have discovered that faster rotation typically produces stronger magnetic fields, but also more unstable ones. Computer models of dynamo action in rapidly spinning planets suggest that Earth's magnetic field might be significantly stronger than our world's field, yet subject to more frequent reversals and excursions. The magnetic poles could wander more, erratically across the planet's surface, sometimes splitting into multiple poles or disappearing entirely for centuries at a time. The rapid rotation also affects the shape of the magnetosphere, that invisible bubble of magnetic influence that deflects charged particles streaming from the Sun. Where our familiar world's magnetosphere forms a relatively stable teardrop shape with a long tail stretching away from the Sun, the moonless Earth's faster rotation would create a more compressed, turbulent magnetic environment. The interaction between solar wind and magnetic field would generate different patterns of charged particle precipitation, altering the aurora displays that paint the polar skies. These auroral phenomena would appear dramatically different from the northern and southern lights we know. The rapid rotation would stretch auroral ovals into thin bands that race across the sky, completing full circuits around the magnetic poles in hours rather than the gradual movements we observe. The compressed magnetosphere would also allow more high-energy particles to penetrate closer to the equator, potentially creating auroras at lower latitudes but with different colors and intensities than our familiar displays. The biological implications of an altered magnetic field extend far beyond mere spectacle. Cosmic radiation, normally deflected by Earth's magnetic shield, would reach the surface in different patterns and intensities. During periods of magnetic field instability, which might occur more frequently due to rapid rotation, the planet would experience increased exposure to harmful radiation from space. This cosmic bombardment could affect the evolution of early life, potentially favoring organisms with enhanced radiation resistance or driving evolution toward deeper, more protected environments. Yet, perhaps the most intriguing aspect of the altered magnetic field lies in its potential effects on atmospheric retention over geological time. The interaction between magnetic field strength, solar wind pressure, and atmospheric escape processes remains incompletely understood even for our own world. Some planetary scientists speculate that a stronger but more variable magnetic field might actually enhance atmospheric loss during periods of field weakness, while providing better protection during stable periods. The mystery deepens when considering how magnetic field variations would affect navigation systems that might develop in any advanced civilizations arising on this world. Compass-based navigation would become far more complex, requiring constant recalibration as magnetic poles wandered, and field strength fluctuated. The relationship between magnetic and geographic poles would remain in constant flux, making long-distance travel and cartography significantly more challenging. Most poetically, the aurora would serve as a visible reminder of the planet's restless magnetic state. Where our world's aurora provide relatively predictable displays tied to solar activity and seasonal variations in magnetic field orientation, the moonless Earth would experience aurora that change character over decades and centuries as the dynamo deep below shifts its magnetic architecture. Only the iron core knows the full complexity of this altered dance, spinning its web of magnetic lines through space with the frantic energy of a world that never learned to slow down, never found the stable rhythm that might nurture the delicate magnetic environment complex life requires. High above the restless surface, in the tenuous layers where atmosphere meets space, a slow catastrophe unfolds over geological time. The solar wind, that constant stream of charged particles flowing from the sun at speeds exceeding 1 million miles per hour, encounters a world less prepared for its erosive embrace. Without the moon's gravitational influence to help retain atmospheric gases, and with a magnetic field that fluctuates more dramatically than our familiar world's steady shield, Earth's upper atmosphere begins to bleed away into the cosmic void. The physics of atmospheric escape operate through several mechanisms that become more pronounced on the moonless world. Thermal escape, where fast-moving gas molecules achieve velocities sufficient to break free of Earth's gravity, increases, with the higher surface temperatures created by rapid rotation and unstable climate patterns. Lighter elements, hydrogen and helium particularly, drift upward through the atmospheric column until they reach altitudes where solar ultraviolet radiation can strip them away entirely. More dramatically, the variable magnetic field creates windows of vulnerability during periods of magnetic pole reversals or field weakening. When the protective magnetic envelope fails, solar wind particles can penetrate deeper into the atmosphere, creating what planetary scientists term polar wind, a process where atmospheric gases are literally sputured away by energetic charged particles. Mars serves as a cautionary example, having lost much of its early atmosphere through such processes after its global magnetic field collapsed. The chemical composition of the escaping atmosphere tells its own story of planetary evolution. Spectroscopic analysis of the thin gas envelope surrounding the moonless Earth would reveal isotopic ratios that differ markedly from our familiar world. Lighter isotopes of hydrogen, carbon, nitrogen, and oxygen preferentially escape to space, leaving behind an atmosphere enriched in heavier isotopes. This isotopic fractionation serves as a signature of atmospheric loss, readable in the chemistry of ancient rocks and ice cores. Over billions of years, this slow hemorrhaging of atmospheric mass would fundamentally alter the planet's surface. Conditions. The greenhouse effect that keeps Earth warm despite its distance from the Sun depends critically on atmospheric composition and density. As water vapor, carbon dioxide, and other greenhouse gases are stripped away, the planet's surface temperature would gradually decline. Paradoxically, a world with more variable climate might ultimately become colder and less hospitable than our stable Earth. Yet the process of atmospheric erosion creates its own mysteries. Some of the escaping gases become ionized in the upper atmosphere, forming plasma that interacts with the magnetic field in complex ways. These interactions can create feedback loops where magnetic field variations enhance atmospheric loss, which in turn affects the planetary environment in ways that influence magnetic field generation. The entire system becomes coupled in patterns that remain difficult to predict even with sophisticated computer models. The irony of atmospheric escape on the moonless world lies in its selectivity. While lighter gases drift away to space, heavier compounds tend to accumulate. The atmosphere might gradually shift toward greater concentrations of noble gases like argon and xenon, chemically inert elements that cannot easily be stripped away by solar radiation. The result would be an atmosphere that becomes less chemically reactive over time, potentially limiting the complex atmospheric chemistry that supports life. Perhaps most poetically, the aurora created by the interaction between solar wind and the variable magnetic field would actually document the ongoing atmospheric loss in real time. The colors and intensities of auroral displays depend partly on which atmospheric gases are being excited by incoming charged particles. As the atmosphere's composition gradually changes, the aurora would slowly shift toward different hues and patterns, creating a celestial record of the planet's slowly diminishing breath. Only the solar wind itself witnesses this patient dismantling, this gradual unbinding of atmospheric molecules from the gravitational embrace that should hold them. The moonless world exhales its substance into space, one atom at a time, like a planet learning to hold its breath but never quite managing to keep what it inhales. The shortened days impose their relentless rhythm on every process that shapes the moonless world's surface. Where our familiar Earth experiences 24-hour cycles that allow gradual temperature transitions between day and night, this rapidly spinning planet endures thermal extremes that would fracture stone and shatter the very foundations of stable climate. 6 hours of daylight bring intense heating, followed immediately by 6 hours of darkness that radiate heat away to space with stunning efficiency. The thermal stress of such rapid cycling creates unique weathering patterns unknown on any slowly rotating world. Rock surfaces expand and contract with each abbreviated day-night cycle, creating stresses that exceed those generated by seasonal temperature variations on our stable Earth. Granite and basalt, normally among the most durable materials in Earth's crust, develop networks of thermal fractures that grow deeper with each cycle. Over geological time, mountain ranges would erode more rapidly, their peaks worn down not by wind and water alone, but by the constant thermal breathing of stone that never finds equilibrium between hot and cold. The atmospheric response to such rapid heating and cooling cycles defies familiar patterns of weather formation. Convective systems that normally develop over hours on our world must instead organize and dissipate within the span of a few hours on the moonless planet. Thunderstorms form with incredible intensity during the heating phase of each short day, then collapse as surface cooling eliminates the thermal energy that drives convection. The result is weather that exists in a perpetual state of formation and decay, never achieving the sustained patterns that create recognizable climate zones. Desert regions experience the most extreme thermal cycling, where surface temperatures, might swing through ranges of 50 to 70 degrees Celsius with each day-night transition. Such temperature variations would create unique geological formations. Rocks split along thermal stress fractures that follow crystalline boundaries, creating landscapes of naturally shattered stone that resembles the aftermath of seismic activity. These thermally fractured terrains would be unlike anything seen on our slowly rotating world. Ocean surfaces respond to the rapid temperature cycling by developing distinct thermal layers that mix and separate with each abbreviated day. Where our familiar seas experience gradual diurnal warming and cooling. The moonless oceans undergo thermal shock that creates vertical circulation patterns lasting only hours. The interface between warm surface water and cooler depths becomes a zone of constant turbulence, preventing the stable thermoclines that normally characterize oceanic structure. Yet perhaps the most intriguing consequence of rapid day-night cycling lies in its effects on photosynthesis and biological rhythms. Plants attempting to adapt to 6-hour days would face the challenge of optimizing light capture and energy storage across cycles too brief for familiar metabolic processes. Photosynthetic organisms might evolve entirely different strategies for managing energy capture and storage, perhaps developing rapid response systems that can quickly adjust to changing light levels. The mystery of how atmospheric chemistry would respond to such rapid temperature cycling remains largely unexplored in planetary science. Chemical reactions that normally proceed at steady rates would experience constant acceleration and deceleration with each thermal cycle. Ozone formation and destruction, water vapor condensation and evaporation, and the oxidation of surface minerals would all operate under conditions of perpetual thermal instability. Most poetically, the rapid temperature changes would create acoustic phenomena unknown on our stable world. Rock fractures formed by thermal stress would generate subtle seismic signals with each heating and cooling cycle. The planet would literally sing with the sound of its own thermal breathing, a percussion section of cracking stone that keeps time with the abbreviated days, creating a geological music that plays in frequencies too low for most life to hear. The irony emerges slowly. A world spinning too fast to know thermal peace would actually experience more regular temperature patterns than our own climate chaotic Earth. Where our world undergoes seemingly random weather variations, the moonless planet would cycle through predictable thermal extremes tied directly to its 6-hour rotation, creating a climate that is harsh but mathematically precise. Only the stones themselves remember each thermal cycle, accumulating stress fractures like tree rings that record the patient passage of abbreviated time, the endless expansion and contraction of a world that never learned to moderate its thermal extremes. Along the static coastlines of the moonless world, the zones where land meets sea remain locked in configurations that would seem impossibly sterile to eyes accustomed to the dynamic intertidal landscapes of our familiar Earth. Where tidal pools should form, those crucial crucibles of evolutionary innovation, only uniform shallow waters persist, neither fully marine nor capable of concentrating the organic chemicals that drive biochemical complexity. The absence of tides eliminates the very laboratory where life typically learns its most important lessons about surviving in multiple environments simultaneously. On our world, tidal pools serve as natural test chambers where organisms must adapt to dramatic changes in salinity, temperature, oxygen levels, and desiccation stress occurring on predictable cycles. These environments favor the evolution of versatile organisms capable of surviving in both aquatic and terrestrial conditions, the very adaptability that eventually enables the transition from sea to land. Without tidal action, the moonless Earth's coastlines lack these evolutionary stepping stones, remaining as simple boundaries between two distinct habitat types that rarely interact. The chemistry of tideless coastal waters develops along fundamentally different pathways. Tidal action normally concentrates dissolved organic compounds through evaporation during low tides, creating pools with elevated concentrations of amino acids, sugars, and other building blocks of life. Without this natural concentration mechanism, coastal waters maintain relatively dilute solutions of organic materials, reducing the probability of complex molecular interactions that might lead to the spontaneous formation of primitive cellular structures. Rock pool formation, normally driven by the mechanical action of waves during high tides followed by isolation during low tides, proceeds through entirely different processes on the tideless world. Coastal erosion creates depressions and cavities in rocky shores, but these remain connected to the sea at a constant level, never experiencing the isolation that allows unique chemical environments to develop. The result is coastal topography that lacks the complex three-dimensional structure characteristic of intertidal zones. Marine organisms attempting to colonize these static shorelines face evolutionary challenges unknown on tidally active worlds. Without the regular cycles of submersion and exposure, there is no selective pressure favoring organisms capable of surviving periodic desiccation, temperature fluctuation, or variable salinity. Coastal life remains fully aquatic, never developing the physiological flexibility that typically precedes terrestrial adaptation. Yet, perhaps the most profound absence lies in the elimination of tidal rhythms from biological evolution. Many marine organisms synchronize their reproductive cycles, feeding behaviors, and metabolic processes to tidal schedules, using these regular environmental cues to coordinate complex life activities. Without tidal rhythms, coastal ecosystems lack this temporal organizing principle, potentially developing along less synchronized and more individually variable evolutionary pathways. The sedimentary geology of tideless coasts preserves different records than familiar shorelines. Tidal action normally creates distinctive layered deposits as sediments are deposited during high tides and reworked during low tides, generating stratified sequences that geologists can read like calendars of ancient environmental conditions. Tideless shores accumulate sediments through wave action alone, creating deposits that lack the rhythmic layering that characterizes intertidal geological formations. And scientists studying the early evolution of life have identified tidal pools as crucial environments for the development of complex organic chemistry. The repeated cycles of concentration through evaporation and dilution through tidal refilling create conditions that favor the formation of long-chain molecules and primitive membrane structures. Without these natural laboratories, the moonless world's path toward life must find alternative routes through the maze of chemical possibility. The acoustic signature of tideless coasts differs markedly from familiar shorelines. The rhythmic sounds of water flowing in and out of tidal channels, the gentle lapping of rising and falling tides, and the dripping of water from exposed rocks during low tide all disappear from the coastal soundscape. Only wind-driven waves provide the music of the sea meeting land, creating shores that speak in monotones rather than the complex harmonies of tidal voices. Most mysteriously, the absence of tidal mixing eliminates the regular exchange of nutrients between shallow coastal waters and the open ocean. Tides normally pump nutrients from deep waters into shallow coastal zones while carrying organic matter from land into marine ecosystems. Without this tidal pumping, coastal productivity might remain limited by nutrient availability, creating marine ecosystems less capable of supporting complex food webs. Only the waves remain to shape these motionless margins, these boundaries between worlds that never learned to breathe with lunar rhythms, forever static in their chemical simplicity. Beneath the surface of the tideless oceans, water masses settle into configurations that would astonish oceanographers, familiar with our dynamically mixed seas. Without the constant stirring action of tidal currents, the moonless world's waters develop pronounced stratification, distinct layers that resist mixing and maintain their chemical identities for centuries, or millennia. Dense, cold water sinks toward the abyssal depths and remains there, isolated from the warmer layers above, creating oceanic environments as segregated as oil and water in a bottle left perfectly still. The physics governing ocean stratification operate through density differences created by temperature and salinity variations. On our familiar world, tidal mixing helps transport nutrients from deep, cold layers to sunlit surface waters where photosynthetic organisms can utilize them. Without this vertical mixing, the moonless oceans develop what oceanographers term permanent thermoclines, thermal boundaries between water masses that persist unchanged across geological time scales, creating vertical zones as distinct as separate worlds. Deep water formation, normally driven by the sinking of cold, dense water at polar regions, continues on the moonless world but with profoundly different consequences. The cold water that forms near the poles and sinks to oceanic depths remains trapped there, accumulating dissolved nutrients from decomposing organic matter that rains down from surface layers. Over thousands of years, these deep waters become enriched with phosphates, nitrates, and silicates, essential nutrients that remain locked away from the productive surface zones where life requires them. The surface layers, deprived of deep water, nutrients gradually become oligotrophic, crystal clear but nearly barren, like vast aquatic deserts floating above treasure troves of chemical wealth they cannot access. Primary productivity in surface waters depends on whatever nutrients can be supplied by rivers, atmospheric deposition, and the slow molecular diffusion across density boundaries. Marine ecosystems in such environments would necessarily develop different strategies for nutrient cycling and energy transfer. Yet, the stratified oceans create their own unique environments within each isolated layer. The deep waters, rich in nutrients but devoid of sunlight, might support chemosynthetic ecosystems similar to those found around hydrothermal vents on our world's seafloor. These deep communities would derive energy from chemical reactions rather than photosynthesis, potentially developing complex food webs based entirely on bacterial primary production, fueled by dissolved nutrients. Between the surface and deep layers, intermediate waters develop distinct characteristics determined by their depth and the balance between temperature and salinity. These mid-depth zones might harbor unique biological communities adapted to conditions of moderate light penetration and moderate nutrient availability. Ecosystems that exist in the twilight between the sunlit surface and the nutrient-rich depths, developing along evolutionary pathways impossible in well-mixed oceans. The mystery of how ocean circulation would operate in such stratified seas remains partly theoretical. While wind-driven surface currents would still transport water around ocean basins, the deep circulation that normally connects all ocean depths would be severely limited. Deep waters formed at polar regions might remain isolated in their basins of origin for millennia, creating oceanic provinces as chemically distinct as separate planets. Perhaps most intriguingly, the lack of vertical mixing might actually preserve a more detailed record of oceanic history than our dynamic seas can maintain. Chemical signatures of past climate conditions, volcanic events, and biological productivity would remain stratified in deep waters like pages in a book, with each layer preserving the dissolved chemistry of its formation period. These oceanic archives might retain environmental records spanning millions of years. The biological implications of oceanic stratification extend far beyond simple nutrient limitation. Marine organisms attempting to migrate vertically through the water column would encounter chemical boundaries as distinct as moving between different atmospheric layers. Fish attempting to dive from surface to deep waters would face changing pressures, temperatures, salinities, and nutrient concentrations that might require physiological adaptations beyond those found in any terrestrial organism. Most poetically, the stratified oceans would create underwater landscapes invisible from the surface, chemical provinces bounded not by mountains or valleys, but by invisible density gradients that separate water masses as effectively as continental barriers, separate terrestrial ecosystems. These liquid continents would drift slowly through the oceanic depths, carrying their distinct chemical signatures across basins and around current systems, maintaining their identities across centuries of slow circulation. Only the patient molecular diffusion at boundary layers allows any exchange between these aquatic provinces, the slowest possible mixing that maintains the ocean's memory of every climate that ever touched its surface. In the chemical soups of the moonless world's ancient seas, the earliest stirrings of life encounter conditions that would seem alien even to the primitive organisms that eventually colonized our familiar Earth. Without tidal rhythms to drive the concentration and dilution cycles that typically foster complex molecular assembly, organic chemistry proceeds along pathways that lack the pulsing temporal structure that biochemists believe crucial for the emergence of self-replicating systems. The building blocks of life, amino acids, nucleotides, and simple sugars, dissolve into oceanic solutions that remain forever mixed at dilute concentrations. The formation of the first protocells, those primitive membrane-bound structures that represent the transition from chemistry to biology, faces unprecedented challenges in tideless environments. On our world, tidal pools provide natural laboratories where organic molecules become concentrated through evaporation, increasing the probability of complex interactions that lead to the spontaneous formation of lipid vesicles and other primitive cellular structures. Without these concentration mechanisms, the moonless oceans must rely on other processes, perhaps hydrothermal vents or volcanic hot springs, to create the chemical gradients necessary for life's emergence. Early metabolic systems attempting to evolve in the stratified oceans encounter the problem of resource distribution that would puzzle any biochemist. Essential elements for life, carbon, nitrogen, phosphorus, and sulfur, become segregated into different oceanic layers with some nutrients trapped in deep waters and others concentrated near the surface. Primitive organisms must either adapt to extremely low nutrient concentrations or evolve complex vertical migration behaviors to access resources distributed across oceanic depth zones. The absence of regular environmental rhythms affects the evolution of biological clocks in ways that remain largely theoretical. On our world, tidal cycles provide external timing cues that help organize cellular processes, metabolic rhythms, and reproductive cycles in even the most primitive organisms. Without these regular environmental pulsations, early life on the moonless world must develop internal timing mechanisms based on other periodicities, perhaps the rapid day-night cycles or the longer-term variations in obliquity and climate. Yet, perhaps most profoundly, the lack of tidal stress eliminates one of the primary drivers of evolutionary innovation that characterizes early life on our world. Organisms in tidal zones must develop mechanisms for surviving rapid changes in temperature, salinity, pH, and oxygen availability, adaptations that create the physiological flexibility later required for colonizing new environments. Without this environmental pressure for versatility, early life might remain more specialized but less adaptable. The genetic implications of tideless evolution extend to the very structure of primitive hereditary systems. Some biochemists speculate that the regular cycles of concentration and dilution provided by tides help stabilize early RNA-based replication systems by providing alternating periods of synthesis and error checking. Without these cycles, primitive genetic systems might develop along different pathways, perhaps favoring simpler but more stable hereditary mechanisms over the complex but versatile systems that eventually gave rise to DNA. Marine microbial communities, attempting to establish themselves in stratified waters, face unique ecological challenges. The formation of microbial mats, those layered communities of different bacterial species that represent some of Earth's earliest ecosystems, requires specific chemical gradients and nutrient flows that are normally maintained by tidal mixing. In tideless oceans, such communities might form at the boundaries between different water masses, creating biological interfaces that exist in three-dimensional rather than two-dimensional configurations. The mystery of how photosynthetic organisms would evolve in stratified oceans remains largely unexplored. The development of oxygenic photosynthesis, the process that eventually transformed Earth's atmosphere and made complex life possible, requires specific combinations of light availability and nutrient concentrations that might be difficult to achieve in permanently stratified waters. Early photosynthetic organisms might remain confined to narrow depth zones where light and nutrients overlap, limiting their evolutionary potential. Perhaps most intriguingly, the absence of tidal rhythms might actually favor the evolution of organisms with more flexible temporal strategies. Without predictable environmental cycles to synchronize with, early life might develop more individualistic approaches to growth, reproduction, and metabolism, creating biological communities that operate with less temporal coordination but greater individual adaptability to changing conditions. The irony of tideless evolution lies in its potential for both limitation and liberation. While the absence of tidal mixing removes many of the environmental pressures that drive evolutionary innovation, it also eliminates the constraints that normally restrict life to specific temporal patterns. The result might be biological systems that evolve more slowly but along more diverse pathways than the tidally influenced life of our familiar world. Only the patient chemistry of dissolving and precipitating minerals witnesses these earliest experiments in biological organization, these molecular assemblages that learn to persist and reproduce in waters that never learn the rhythmic breathing that normally guides life's first tentative steps toward complexity. Deep within the cellular architecture of life attempting to evolve on the moonless world, the absence of lunar rhythms creates a temporal vacuum that organisms must somehow learn to fill. Where life on our familiar Earth synchronizes its most fundamental processes to the 29-day lunar cycle, from reproductive hormones to metabolic oscillations, the organisms of the tideless world must construct their biological clocks from entirely different celestial materials. The rapid 6-hour day-night cycles provide one temporal cue, but these brief oscillations lack the longer periodicities that typically organize complex life processes. The evolution of circadian rhythms, those internal 24-hour clocks that govern everything from sleep cycles to hormone production in terrestrial organisms, faces unprecedented challenges when the actual day lasts only 6 hours. Biological systems attempting to maintain internal rhythms that differ from environmental light-dark cycles must evolve robust molecular clockwork capable of ignoring external cues, or, alternatively, must adapt to the rapid tempo of abbreviated days in ways that would fundamentally alter the nature of biological timekeeping. Marine organisms that might evolve in the stratified oceans lack the regular tidal cues that normally coordinate spawning, feeding, and migration behaviors. Many marine species on our world time their reproduction to specific tidal conditions, releasing eggs and sperm during particular tide phases, or timing larval release to maximize dispersal by tidal currents. Without these predictable environmental rhythms, marine life must develop alternative strategies for synchronizing reproductive activities across populations. The absence of lunar cycles affects not only the timing of biological processes, but also their fundamental organization. Lunar periodicity provides a natural calendar that spans the gap between daily circadian rhythms and annual seasonal cycles, allowing organisms to organize complex behaviors, such as long-distance migrations or multi-week reproductive cycles, within predictable temporal frameworks. Without lunar months, biological systems must either compress complex processes into daily cycles or extend them to seasonal timescales, eliminating intermediate temporal strategies. Yet perhaps the most profound consequence of missing lunar rhythms lies in the evolution of biological synchrony itself. Many ecological processes depend on the coordinated behavior of multiple individuals or species, predator-prey relationships, pollination events, and competitive interactions require temporal coordination that lunar cycles normally provide. Without this universal biological metronome, ecosystems might develop less synchronized interaction networks, potentially reducing the efficiency of energy transfer and nutrient cycling. The molecular mechanisms underlying biological clocks face unique evolutionary pressures on a world without lunar guidance. Clock proteins and genetic regulatory networks normally maintain complex relationships between daily, lunar, and seasonal timing systems. In the absence of lunar cues, these molecular clockwork systems might evolve simplified architectures focused primarily on circadian or seasonal rhythms, potentially losing the temporal complexity that characterizes biological timing in our familiar world. Reproductive cycles present particularly intriguing evolutionary challenges. Many organisms on our world coordinate their reproductive activities, with lunar phases to maximize fertilization success, larval survival, or parental care efficiency. Female mammals, including humans, show reproductive cycles that approximately match lunar periods, though the causal relationships remain debated among biologists. Without lunar periodicities, reproductive timing might synchronize to seasonal variations, solar activity cycles, or entirely internal biological rhythms. The development of migration behaviors would necessarily follow different pathways on the moonless world. Many migratory species use lunar phase as a timing cue for initiating long-distance journeys, ensuring that arrivals at breeding or feeding grounds coincide with optimal environmental conditions. Without lunar calendars, migratory organisms must rely on other environmental cues, temperature changes, day-length variations, or resource availability to time their movements across seasons and landscapes. Perhaps most mysteriously, the absence of lunar rhythms might affect the evolution of consciousness and complex behavior in ways that remain purely speculative. Some researchers have suggested that lunar cycles influence sleep patterns, dreaming, and cognitive functions in humans and other mammals, though the mechanisms remain unclear. If lunar rhythms do affect neural development and brain function, their absence might lead to the evolution of nervous systems with different architectures and capabilities. The irony of clockless biological evolution becomes apparent when considering that organisms might actually develop more precise internal timing systems in the absence of external lunar cues. Without the option of synchronizing to lunar phases, biological clocks must become more accurate and reliable, potentially leading to the evolution of molecular timepieces superior to those found in lunar-influenced organisms. Only the patient. Accumulation of seasonal variations provides any long-term temporal structure to life that must learn to keep time without the moon's ancient metronome, creating biological communities that march to rhythms of their own devising, forever improvising temporal patterns in the silence where lunar music should play. In the shallow seas surrounding what would be tropical islands on the moonless world, the absence of tidal rhythms prevents one of Earth's most spectacular evolutionary achievements from ever taking root. Coral reefs, those underwater cities built by countless generations of tiny polyps working in partnership with symbiotic algae, require the precise environmental conditions that only tidal zones can provide. Without the regular ebb and flow of tides to deliver nutrients, remove waste products, and create the complex three-dimensional structures that support reef ecosystems, the warm shallows remain bare of the calcium carbonate cities that normally transform tropical coastlines into underwater rainforests. The biology of coral reef formation depends critically on tidal processes that remain absent from the moonless world's static shorelines. Coral polyps require regular water circulation to deliver microscopic food particles and dissolved nutrients while carrying away metabolic waste products. Tidal currents provide this circulation naturally, creating flows that flush reef systems twice daily and prevent the accumulation of sediments that would otherwise smother coral colonies. Without tidal flushing, tropical shallows become stagnant environments where organic matter decomposes in place, creating conditions hostile to the delicate chemistry required for calcium carbonate precipitation. The symbiotic relationship between corals and zooxanthellae, The photosynthetic algae that live within coral tissues and provide most of their energy faces additional challenges in tideless waters. These algal symbionts require specific light conditions and water chemistry to maintain optimal photosynthetic rates. Tidal mixing normally helps maintain water clarity and nutrient balance within the narrow ranges required for successful coral-algae partnerships. In stagnant, shallow waters, algal blooms and sediment accumulation would create turbid conditions that block sunlight and disrupt the delicate metabolic balance between host and symbiont. The three-dimensional architecture that makes coral reefs among the most biodiverse ecosystems on our planet cannot develop without the hydraulic forces that tidal action provides. Coral growth responds directly to water flow patterns, with different species adapting to different current regimes. Brain corals develop their convoluted surfaces to maximize water flow across feeding polyps, while branching corals create complex structures that channel currents through their colonies. Without tidal currents to provide consistent flow patterns, coral architecture would lack the diversity of forms that creates habitat complexity. Marine organisms that depend on coral reef ecosystems for shelter, breeding grounds, and feeding opportunities would never evolve on the moonless world. Reef fish, which represent some of the most colorful and diverse vertebrate communities on our planet, require the complex three-dimensional habitat that coral formations provide. The absence of reefs eliminates entire evolutionary pathways that lead to specialized feeding strategies, complex social behaviors, and the brilliant coloration patterns that characterize tropical marine fish communities. Yet, perhaps most profoundly, the absence of coral reefs eliminates one of the ocean's most important carbon cycling mechanisms. Coral reefs actively remove dissolved carbon dioxide from seawater through the precipitation of calcium carbonate skeletons, helping regulate oceanic pH and atmospheric carbon dioxide concentrations. Without reef systems, the moonless world's oceans would maintain different chemical compositions, potentially affecting global climate regulation and the evolution of carbonate chemistry throughout geological time. The geological consequences of missing coral reefs extend far beyond biology. Coral reefs create massive limestone formations that influence coastal geology, wave patterns, and sediment transport. These biological rock formations protect coastlines from wave erosion and create unique geological structures that preserve detailed records of past sea levels and climate conditions. Without coral reefs, tropical coastlines would erode more rapidly and preserve different types of geological records in their sedimentary formations. Scientists studying the evolution of reef ecosystems have identified several critical threshold conditions required for reef development. Water temperature, salinity, nutrient levels, light availability, and water circulation must all remain within narrow ranges for extended periods. The absence of tidal mixing makes it unlikely that all these conditions could be maintained simultaneously in any location for the thousands of years required for significant reef development. The acoustic environment of tropical waters would differ markedly without coral reefs. Reef ecosystems generate complex soundscapes through the activities of countless fish, crustaceans, and other marine organisms. The crackling sounds of snapping shrimp, the grunting calls of reef fish, and the mechanical noises of organisms drilling into coral skeletons create underwater soundscapes that can be heard kilometers away. Without reefs, tropical seas would remain acoustically simple, lacking the biological cacophony that characterizes healthy reef ecosystems. Perhaps most poetically, the absence of coral reefs eliminates one of nature's most impressive examples of biological construction. Coral colonies represent some of the largest biological structures on our planet, with individual reef systems extending across hundreds of kilometers and consisting of countless trillions of interconnected organisms. These living cities demonstrate the power of biological processes to reshape entire landscapes through the accumulated efforts of microscopic builders working across geological time scales. Only the empty tropical shallows remain, waters that warm under the sun but never learn the architectural ambitions of tiny polyps, forever clear but barren in their tideless simplicity. Along the continental margins of the moonless world, the shallow seas that should teem with evolutionary innovation remain trapped in configurations that would puzzle any marine biologist. Continental shelves, those underwater plains that extend from coastlines toward the deep ocean basins, lack the dynamic processes that normally make them among the most productive and biodiverse marine environments on our planet. Without tidal currents to mix nutrients from deep waters with sunlight-rich surface layers, these vast, shallow regions become oceanic deserts, clear and beautiful, but largely empty of the complex food webs that characterize familiar shelf ecosystems. The absence of tidal pumping eliminates the regular upwelling of nutrient-rich deep water that normally fertilizes continental shelf waters. On our world, tidal currents flowing over shallow topography create vertical mixing that brings nitrates, phosphates, and other essential nutrients from the seafloor into the euphotic zone where photosynthetic organisms can utilize them. Without this tidal fertilization, shelf waters remain oligotrophic, nutrient-poor environments that can support only sparse populations of specially adapted organisms capable of surviving in aquatic equivalents of high-altitude deserts. The sedimentary geology of tideless continental shelves develops along fundamentally different pathways than familiar shallow seas. Tidal currents normally transport sediments in complex patterns, creating the varied bottom topography, ripple marks, sand waves, and sediment sorting patterns that provides diverse habitats for bottom-dwelling organisms. Without tidal transport, shelf sediments accumulate primarily through river discharge and wind-driven currents, creating more uniform bottom conditions that lack the habitat complexity required for diverse benthic communities. Upwelling systems, those crucial oceanic phenomena where deep, nutrient-rich waters rise to the surface and support some of the most productive marine ecosystems on our planet, operate under severely limited conditions on the moonless world. While wind-driven upwelling can still occur along some continental margins, the absence of tidal mixing reduces the efficiency of vertical nutrient transport. Upwelling regions that should support massive populations of plankton, fish, and marine mammals instead become moderately productive at best, unable to sustain the abundant marine life that characterizes similar regions in our familiar oceans. The evolution of filter-feeding organisms faces unique challenges in nutrient-poor shelf waters. Clams, oysters, and other bivalve mollusks that normally thrive in shallow coastal waters by filtering microscopic food particles from the water column would struggle to obtain sufficient nutrition in the clear but sparse waters of tideless shelves. The absence of regular tidal flushing also eliminates the delivery of organic matter from terrestrial sources that normally supports filter-feeding communities. Yet, perhaps most significantly, the lack of tidal energy eliminates one of the primary mechanisms that drives larval transport and genetic exchange between marine populations. Many marine organisms release their offspring as planktonic larvae that depend on tidal currents for dispersal to suitable habitat. Without predictable tidal transport, marine populations become more isolated, potentially leading to increased speciation, but reduced genetic diversity within local populations. The absence of estuarine environments, those crucial mixing zones, where rivers meet the sea, profoundly affects the continental shelf ecosystems. Estuaries normally serve as nursery grounds for many marine species, providing protected environments with intermediate salinities that juvenile organisms require for development. Without tidal mixing to create and maintain estuarine conditions, the transition from fresh to saltwater occurs more abruptly, eliminating habitat zones that support specialized brackish water communities. Bottom-dwelling communities that depend on organic matter settling from surface waters face different resource availability patterns on tideless shelves. Without tidal resuspension of sediments and organic particles, the rain of organic matter from surface waters follows patterns determined primarily by seasonal productivity cycles and ocean currents. This might create more patchy resource distribution on the seafloor, with some areas receiving abundant organic input while others remain nearly barren. The mystery of how deep-sea organisms would interact with continental shelf ecosystems remains, largely theoretical. Many deep-sea species on our world undergo vertical migrations that bring them into shallow water during specific tidal phases, creating connections between deep and shallow marine communities. Without tidal cues, these vertical migration patterns might not evolve, potentially reducing the ecological connectivity between different depth zones. Perhaps, most poetically, the continental shelves of the moonless world would represent vast, underwater prairies, expanses of shallow seafloor that extend for hundreds of kilometers from continental margins, covered by sparse communities of organisms adapted to nutrient-poor conditions. These marine grasslands would possess their own subtle beauty, with widely spaced organisms existing in the clear blue twilight of deep shelf waters, but they would lack the dense biological communities that make familiar continental shelves, among the most productive ecosystems on our planet. The irony of these quiet shelves lies in their potential for preserving detailed geological records. Without the constant reworking of sediments by tidal currents, continental shelf deposits might maintain more complete stratigraphic sequences, creating underwater libraries of environmental history that could be read by future geologists with unprecedented clarity and temporal resolution. Only the slow accumulation of sediments marks the passage of time across these underwater plains, continental margins that never learned the restless productivity that tidal energy normally brings to the boundary zones between land and sea. In the perpetual darkness that falls across the moonless world each night, the absence of lunar illumination creates evolutionary pressures that would reshape the very nature of vision and nocturnal adaptation. Where our familiar Earth bathes in the gentle silver light that reflects from the moon's ancient surface, illumination bright enough to read by during full moon nights, this world knows only the faint starlight that filters through atmospheric layers, creating darkness so complete that visual evolution must follow entirely different pathways. The night sky offers no reliable source of reflected sunlight, no pale companion to cast shadows or illuminate the landscape with borrowed radiance. The physics of available nighttime illumination on the moonless world would challenge any organism attempting to evolve sophisticated visual systems. Starlight provides roughly 10,000 times less illumination than moonlight, creating light levels that approach the theoretical limits of biological photoreception. Even the most sensitive visual systems that evolution has produced on our world, such as the compound eyes of nocturnal moths or the enlarged pupils of deep-sea fish, would struggle to function effectively under such extreme light limitation. Nocturnal. Animals attempting to navigate this darker world would necessarily evolve enhanced non-visual sensory capabilities. Echolocation systems, normally found only in specialized groups like bats and dolphins, might become more common among terrestrial animals. The development of sophisticated sound-based navigation would likely drive the evolution of more complex auditory processing systems, creating nocturnal communities that communicate and navigate through acoustic rather than visual channels. The evolution of bioluminescence, the ability of living organisms to produce their own light through chemical reactions, would face different selective pressures on the moonless world. While bioluminescent organisms exist in the dark depths of our oceans and in some terrestrial environments, the complete absence of moonlight might make biological light production more advantageous for a broader range of organisms. Terrestrial animals might evolve bioluminescent communication systems that would remain invisible on our moonlit world, but become essential signaling mechanisms in perpetual darkness. Plant evolution would follow dramatically different pathways, in the absence of any significant nighttime illumination. Many plants on our world respond to moonlight cycles, using the regular variations in nighttime brightness to regulate flowering, seed germination, and growth patterns. Without these lunar cues, Plant reproductive strategies would need to synchronize through other environmental signals, temperature variations, humidity changes, or chemical communication through root systems and atmospheric compounds. The development of enhanced chemoreception, the ability to detect and interpret chemical signals through smell and taste, would likely become more pronounced among nocturnal organisms. Many animals on our world already rely heavily on chemical communication during dark periods, but the complete absence of visual cues would place even greater evolutionary pressure on the development of sophisticated chemical sensing systems. Scent trails, pheromone communication, and chemical territory marking might become the primary means of nocturnal interaction. Yet, perhaps the most intriguing aspect of evolution in perpetual darkness lies in the potential development of entirely novel sensory modalities. Some scientists speculate that organisms might evolve enhanced sensitivity to electromagnetic fields, infrared radiation, or even subtle vibrations transmitted through air or ground. The evolutionary creativity that produces echolocation in bats and electroreception in sharks might generate sensory capabilities that remain unknown in our moonlit world. The behavioral ecology of nocturnal communities would develop along unique pathways without visual cues to coordinate social interactions. Many nocturnal animals on our world use moonlight to coordinate mating displays, territorial behaviors, and predator-prey interactions. In the complete darkness of the moonless world, these behaviors would need to operate through acoustic, chemical, or tactile communication channels, potentially creating more intimate but less spatially extensive social networks. Predator-prey relationships would evolve under fundamentally different conditions when neither predators nor prey can rely on visual detection systems. The evolutionary arms race between predators trying to locate prey and prey trying to avoid detection would focus on non-visual sensory modalities, potentially leading to the evolution of organisms with extraordinary auditory acuity, chemical detection sensitivity, or vibrational awareness that would seem supernatural to creatures evolved under moonlit skies. The mystery of how complex visual systems would eventually evolve in such environments remains fascinating to consider. Vision requires significant evolutionary investment in neural processing systems and metabolic energy, investments that might not be justified in environments with extremely limited light availability. Organisms might instead evolve highly efficient visual systems that function only during brief dawn and dusk periods, remaining essentially blind during the long nights. Perhaps most poetically, the night sounds of the moonless world would develop into complex acoustic landscapes unknown in our familiar environment. Without the visual cues that normally coordinate nocturnal activities, the darkness would fill with elaborate sound patterns, echolocation calls, territorial songs, mating displays, and alarm signals creating symphonies of survival, played in frequencies that span the entire auditory spectrum. The irony of this darker evolution lies in its potential for creating organisms with sensory capabilities that exceed those found in our moonlit world. The necessity of functioning in complete darkness might drive the development of sensory systems so sophisticated that they would seem like supernatural abilities to creatures accustomed to the luxury of reflected moonlight. Only the stars themselves witness these adaptations to perpetual darkness, these organisms learning to navigate and communicate in a world where the night holds no silver comfort, no borrowed light to ease the transition from day's harsh brightness to darkness absolute and unrelenting. In the shallow waters where sea meets land on the moonless world, the great evolutionary transition from aquatic to terrestrial life encounters obstacles that would fundamentally alter the history of vertebrate development. Without tidal cues to guide the precise timing of spawning events, early vertebrates attempting to colonize coastal environments lack the environmental signals that normally coordinate reproductive cycles with optimal conditions for larval survival. The absence of predictable water level changes eliminates the natural nurseries that tidal pools and estuarine environments typically provide for developing vertebrate young. the evolution of anadromous behaviors, the remarkable life strategies. Where organisms like salmon spend adult lives in marine environments but return to freshwater streams for reproduction, faces unprecedented challenges without tidal guidance. These complex reproductive migrations depend critically on tidal timing to navigate coastal waters, enter river mouths, and coordinate spawning activities with seasonal freshwater conditions. Without tidal cues, such precisely timed reproductive strategies might never evolve, eliminating entire categories of vertebrate life histories that depend on coordinated movement between marine and freshwater environments. Early vertebrates attempting to develop air-breathing capabilities would lack the environmental pressures that tidal zones normally provide. The regular exposure and submersion cycles in tidal pools create strong selective pressures favoring organisms capable of surviving in both aquatic and aerial environments, the evolutionary stepping stones that typically lead to the development of primitive lungs and eventually to full terrestrial adaptation. Without these intermediate environments, the transition from water breathing to air breathing would require different evolutionary pathways. The development of limbs capable of terrestrial locomotion faces different selective pressures in the absence of tidal zones. Many early tetrapods on our world evolved strengthened fins and eventually primitive limbs as adaptations for moving through shallow tidal waters and temporarily stranded pools. Without these environments, vertebrate locomotion might evolve along different trajectories, perhaps favoring more efficient swimming adaptations or developing terrestrial locomotion through entirely different mechanical solutions. Spawning behaviors that depend on precise environmental timing would necessarily develop alternative strategies on the moonless world. Many fish species synchronize their reproductive activities with specific tidal conditions, releasing gametes during particular tide phases, constructing nests in areas that will be exposed during low tides for optimal oxygen exposure, or timing. Larval release to coincide with tidal transport patterns. Without these environmental cues, reproductive timing would need to synchronize with other periodicities or develop more flexible, opportunistic strategies. Yet, perhaps most significantly, the absence of tidal mixing eliminates the creation of brackish water environments, those crucial intermediate zones where salinity gradually transitions from freshwater to marine conditions. Many vertebrate groups require these intermediate environments for osmoregulatory adaptation, gradually adjusting their internal salt balance as they move between different aquatic environments. Without brackish zones, the physiological transition from freshwater to marine environments becomes more challenging. The evolution of complex life cycles that involve metamorphosis between aquatic larvae and terrestrial adults would face different constraints without tidal environments. Amphibians, which typically require shallow temporary water bodies for reproduction and larval development, would need to find alternative breeding environments. The absence of tidal pools and regularly flooded coastal areas might favor the evolution of different reproductive strategies, perhaps internal fertilization and direct development, or the utilization of entirely different aquatic environments for reproduction. Marine vertebrates attempting to develop enhanced sensory capabilities for navigation would lack one of the most reliable environmental cues available to aquatic organisms. Many marine animals use tidal patterns for navigation, timing their movements to coincide with favorable tidal conditions for feeding, reproduction, or migration. Without tidal rhythms, marine navigation would need to rely more heavily on other environmental cues, magnetic fields, water temperature gradients, or chemical gradients, potentially driving the evolution of more sophisticated non-tidal navigation systems. The development of parental care behaviors in aquatic environments might follow different evolutionary pathways without tidal timing cues. Many fish species on our world time their nest building and parental care activities to tidal cycles, ensuring that developing eggs and larvae receive optimal water circulation and protection. Without predictable environmental cycles, parental care strategies would need to become more flexible or rely on different environmental indicators of optimal conditions. Perhaps most mysteriously, the evolution of complex social behaviors in coastal vertebrate communities might develop differently, without the regular congregation opportunities that tidal cycles provide. Many marine animals use predictable tidal conditions for social interactions, feeding aggregations during optimal tidal phases, reproductive gatherings timed to tidal cycles, or territorial behaviors synchronized with tidal patterns. Without these regular social opportunities, vertebrate communities might develop less coordinated but more individually flexible social strategies. The irony of untimed vertebrate evolution becomes apparent when considering that organisms might actually develop more robust, less environmentally dependent life strategies in the absence of tidal cues. Without the option of synchronizing reproductive and developmental activities to predictable environmental cycles, vertebrates might evolve more flexible, opportunistic life histories that prove more resilient to environmental variation over geological timescales. Only the patient flow of rivers meeting the sea marks the boundary between aquatic and terrestrial realms, boundaries that never pulse with tidal rhythms, never provide the environmental metronome that typically guides vertebrate evolution through its most crucial transitions from water-dwelling to land-walking life. In the shallow waters and coastal margins of the moonless world, the plant kingdom's great evolutionary leap from aquatic to terrestrial environments encounters barriers that would fundamentally reshape the history of life on land. Without tidal action to create the specialized environmental conditions that normally ease this transition, early plants attempting to colonize terrestrial environments lack the gradual salinity transitions, regular wet-dry cycles, and protected intermediate zones that typically serve as evolutionary stepping stones between fully aquatic and fully terrestrial existence. The evolution of specialized tissues for water transport, xylem and phloem, faces different selective pressures without the environmental gradients that tidal zones provide. These vascular systems normally evolve in response to the challenge of surviving periodic desiccation in intertidal environments, where plants must efficiently transport water from roots to aerial portions during low tide exposure. Without regular desiccation stress, early plant evolution might proceed along different pathways, perhaps developing alternative strategies for managing water balance and nutrient transport. Reproductive strategies in early terrestrial plants would necessarily develop without the dispersal mechanisms that tidal action typically provides. Many primitive plants on our world rely on water for sperm transport and spore dispersal, utilizing tidal currents to carry reproductive cells between individuals and to new colonization sites. Without predictable water movement patterns, plant reproduction might remain more localized, potentially reducing genetic exchange between populations and slowing the rate of evolutionary innovation. The development of structural support systems, the lignified tissues that allow plants to grow upright against gravity, might follow different evolutionary pathways without the mechanical stresses that wave and tidal action normally impose on coastal vegetation. Plants attempting to colonize the terrestrial environment would need to develop structural support primarily for gravitational loads, rather than the dynamic mechanical forces that coastal plants typically experience, potentially resulting in different architectural solutions for terrestrial growth. Root system evolution faces unique challenges in the absence of regularly fluctuating water tables that tidal action creates. Many coastal plants develop specialized root architectures that can function efficiently in both waterlogged and well-drained soils as tidal cycles alternately flood and drain coastal sediments. Without these fluctuating conditions, root systems might remain more specialized for either aquatic or terrestrial conditions, making the transition between environments more difficult. Yet, perhaps most significantly, the absence of tidal mixing eliminates the regular delivery of marine nutrients to coastal soils that normally supports early terrestrial plant communities. Tidal action typically deposits organic matter, dissolved nutrients, and essential minerals in coastal zones, creating fertile environments where terrestrial plant communities can establish. Without this natural fertilization process, coastal soils might remain nutrient-poor and less suitable for supporting diverse plant communities. The evolution of photosynthetic efficiency faces different optimization pressures without the light environment fluctuations that tidal cycles create. Plants in tidal zones must adapt to rapidly changing light conditions as water levels rise and fall, creating selective pressures for flexible photosynthetic systems. Without these dynamic light environments, early terrestrial plants might develop more specialized but less adaptable photosynthetic machinery. Seed dispersal mechanisms would necessarily evolve without the long-distance transport capabilities that tidal and coastal currents normally provide. Many coastal and early terrestrial plants utilize water-based dispersal strategies, with seeds or spores designed to survive transport by tidal currents to new colonization sites. Without reliable water-based dispersal, plant communities might remain more geographically isolated, potentially leading to increased speciation but slower colonization of new terrestrial environments. The development of tolerance for salinity. Variations, a crucial adaptation for plants transitioning from marine to terrestrial environments, faces different evolutionary pressures without the gradual salinity gradients that estuarine and tidal environments create. Plants attempting terrestrial colonization would need to evolve salt tolerance mechanisms without the benefit of intermediate environments where such adaptations normally develop gradually. Perhaps most intriguingly, the timing of plant reproductive cycles might develop along entirely different temporal frameworks without lunar and tidal cues. Many marine and coastal plants synchronize their reproductive activities with tidal cycles, ensuring optimal conditions for gamete release, fertilization, and dispersal. Without these environmental timing cues, plant reproductive cycles might synchronize with other environmental periodicities or develop more flexible, opportunistic timing strategies. The formation of complex plant communities that include both aquatic and terrestrial species would face different organizational challenges without the habitat gradients that tidal zones create. Coastal plant communities normally develop as a series of vegetation zones adapted to different frequencies and durations of tidal flooding. Without these environmental gradients, plant communities might develop sharper transitions between aquatic and terrestrial zones, with fewer species adapted to intermediate conditions. The mystery of how complex terrestrial ecosystems would eventually develop without the colonization pathways that coastal environments normally provide remains fascinating to consider. The absence of tidal zones might delay terrestrial colonization significantly, potentially altering the entire trajectory of evolution by keeping complex plant communities restricted to aquatic environments for much longer periods. Perhaps most poetically, the shores of the moonless world would lack the green gradients that normally mark the transition from sea to land, the salt marshes, mangrove forests, and coastal vegetation that create living bridges between aquatic and terrestrial realms. Instead, these boundaries might remain more sharply defined, with fully aquatic plant communities ending abruptly at shorelines where terrestrial vegetation begins, creating landscapes that lack the gentle gradations that tidal action normally provides. Only the patient lapping of wind-blown waves marks these static boundaries. Coastlines where plants never learn to venture gradually from sea to land, forever hesitating at the edges of evolutionary possibility. In the hypothetical civilizations that might eventually arise on the moonless world, the absence of lunar phases eliminates one of humanity's most fundamental tools for organizing time itself. Without the reliable 29-day cycle that has provided the basis for calendars throughout human history, early agricultural societies would need to develop entirely different systems for tracking seasonal changes, coordinating social activities, and predicting optimal planting and harvesting times. The very concept of months, those convenient divisions of time that bridge the gap between daily experience and annual cycles, would never emerge in human consciousness. The development of agriculture faces unprecedented challenges without lunar timing cues that normally help coordinate planting and harvesting activities. Many agricultural societies on our world have traditionally used lunar phases to time crucial farming activities, planting seeds during specific moon phases, harvesting crops when lunar conditions optimize plant moisture content, and timing livestock breeding to coordinate with seasonal lunar cycles. Without these celestial guides, agricultural timing would need to rely entirely on seasonal cues like temperature changes, daylight duration, and precipitation patterns. Early mathematical and astronomical systems would develop along fundamentally different pathways without the regular lunar periodicities that normally provide natural units for mathematical calculation. The number systems that emerged in many human cultures reflect lunar counting, months divided into weeks, seasonal cycles based on lunar quarters, and numerical systems that incorporate lunar-based calculations. Without lunar mathematics, human numbering systems might develop different organizational principles, perhaps based entirely on solar observations or stellar patterns. Religious and philosophical systems would necessarily evolve without the profound symbolic influence that lunar cycles have provided throughout human history. The moon's regular phases of death and rebirth, its association with feminine cycles and agricultural fertility, and its role as a celestial timekeeper have influenced virtually every human culture's mythology and spiritual practices. Without lunar symbolism, human religious thought might develop different metaphorical frameworks for understanding cycles of death and renewal, perhaps drawing inspiration from seasonal changes or stellar patterns. The development of navigation. Techniques would face extraordinary challenges without lunar phases to provide timing references for celestial navigation. Seafaring cultures normally use lunar observations combined with stellar positions to determine location and direction during ocean voyages. Without predictable lunar phases, maritime navigation would need to rely entirely on stellar observations, solar positioning, and environmental cues like wind patterns and ocean currents, making long-distance sea travel significantly more difficult and dangerous. Yet, perhaps most profoundly, the human experience of time itself would develop different psychological and cultural characteristics without the monthly rhythm that lunar cycles provide. The lunar month creates a natural temporal unit that fits comfortably within human attention spans, long enough to encompass complex projects and planning cycles, yet short enough to maintain psychological continuity. Without monthly divisions, human temporal experience might organize around either daily routines or seasonal cycles, potentially creating different relationships between individual experience and social coordination. Social organization and cultural institutions would develop different structural principles without lunar timing to coordinate community activities. Many traditional societies use lunar phases to schedule markets, festivals, religious observances, and social gatherings. The absence of lunar calendars might favor more localized timing systems based on agricultural seasons, weather patterns, or other regional environmental cues, potentially creating more geographically diverse cultural practices. The development of written language and record-keeping systems might follow different pathways without lunar cycles to provide natural organizational frameworks for temporal notation. Many early writing systems incorporate lunar symbols and counting systems, using moon-based calendars to record historical events and coordinate social activities. Without lunar references, written records might organize around different temporal frameworks, perhaps developing more sophisticated seasonal or stellar notation systems. Medical and biological understanding would necessarily develop without the observations of lunar influences on biological rhythms that have informed traditional healing practices throughout human history. Many traditional medical systems incorporate lunar timing for therapeutic interventions, surgical procedures, and herbal preparations. Without lunar cycles, medical knowledge would develop different frameworks for understanding biological rhythms and optimal timing for health interventions. Perhaps most intriguingly, the development of scientific astronomy would follow different historical pathways without the obvious celestial laboratory that lunar phases normally provide. The Moon's regular changes offer easily observable evidence of celestial mechanics, orbital relationships, and the three-dimensional nature of celestial objects. Without lunar phases to study, early astronomers might develop different approaches to understanding planetary motion and celestial mechanics. The mystery of how human creativity and artistic expression would develop without lunar inspiration remains fascinating to consider. Poetry, music, visual arts, and storytelling traditions have drawn extensively on lunar imagery throughout human history. The absence of lunar symbolism might lead to artistic traditions that explore different metaphorical territories, perhaps finding inspiration in stellar patterns, seasonal changes, or the rapid day-night cycles of the 6-hour world. Perhaps most poetically, the languages that developed on the moonless world would lack the extensive vocabulary that lunar observations have provided to human speech. Words for lunar phases, month-based temporal expressions, and the countless metaphors drawn from lunar cycles would never enter human consciousness, creating languages that organize temporal expression around entirely different celestial and environmental references. Only the stars themselves provide celestial punctuation for human timekeeping, constellations that wheel overhead with seasonal regularity but offer no convenient monthly divisions to organize the complex temporal architecture that human civilization requires for its social coordination and cultural development. Across the vast oceans of the moonless world, the development of maritime exploration encounters obstacles that would fundamentally alter the course of human civilization. Without tidal predictions to guide the timing of harbor departures and arrivals, early seafarers attempting to navigate coastal waters lack one of the most reliable tools that maritime cultures have used throughout history: the absence of predictable tidal ranges eliminates the natural harbors, protected anchorages, and navigable channels that tidal action typically creates and maintains along coastlines worldwide. The evolution of shipbuilding technology would follow entirely different pathways, without the engineering challenges that tidal environments normally impose. Traditional boat designs incorporate features specifically adapted to tidal conditions: shallow drafts for navigating tidal flats, flexible construction to withstand beaching during low tides, and hull shapes optimized for the varying water conditions that tidal cycles create. Without these environmental pressures, maritime technology might develop along different trajectories, perhaps emphasizing deep water capabilities over the versatility required for tidal navigation. Coastal settlements would necessarily develop different relationships with the sea without the regular rhythm of tidal changes that normally determines optimal locations for ports, fishing villages, and maritime commerce. Many coastal communities on our world time their daily activities around tidal schedules, launching fishing boats during optimal tides, loading and unloading cargo when harbor depths permit, and conducting maritime maintenance work during low tide exposure. Without tidal timing, coastal life would organize around different environmental cues and constraints. The development of astronomical navigation faces unprecedented challenges without lunar phases to provide temporal references for celestial observations. Traditional navigation techniques rely heavily on the relationship between lunar phases, tidal timing, and stellar positions to determine location and direction during ocean voyages. Ancient mariners used lunar calendars to predict seasonal wind patterns, coordinate long-distance voyages with favorable weather conditions, and maintain temporal orientation during extended periods at sea. Fishing practices and marine resource management would develop along fundamentally different lines without tidal cycles to concentrate fish populations and marine organisms in predictable locations. Many traditional fishing cultures time their activities to tidal movements that bring fish into shallow waters, concentrate shellfish in accessible areas, and create feeding opportunities for marine organisms. Without tidal aggregation effects, fishing communities would need to develop different strategies for locating and harvesting marine resources. Yet, perhaps most significantly, the absence of tidal ranges eliminates the natural phenomena that typically guide mariners in approaching unfamiliar coastlines. Experienced navigators normally use tidal observations to assess water depths, identify safe anchorages, and time approaches to harbors and river mouths. Without tidal indicators, coastal navigation becomes more dependent on visual cues and local knowledge, making exploration of unknown coastlines significantly more dangerous. The development of maritime trade networks would face different logistical challenges without tidal timing to coordinate cargo handling and fleet movements. Traditional maritime commerce relies heavily on tidal schedules to move large vessels through restricted channels, load and unload cargo in harbors with limited depth, and coordinate the complex logistics of multi-vessel trading expeditions. Without predictable tidal windows, maritime trade might remain more limited in scale and geographic scope. Ocean current patterns that drive long-distance navigation would operate under different dynamics without tidal mixing to enhance or modify. Major current systems. While wind-driven currents would still exist, the absence of tidal influences might create more stable but less variable current patterns, potentially making long-distance navigation more predictable but eliminating some of the dynamic current. Systems that experienced navigators typically exploit for efficient ocean passage. The psychology of maritime exploration would develop different characteristics without the temporal security that lunar phases and tidal predictions normally provide to ocean voyagers. The ability to predict tidal conditions days or weeks in advance gives mariners a sense of temporal orientation and environmental predictability that reduces the psychological stress of long-distance voyaging. Without these reliable environmental rhythms, ocean travel might seem more chaotic and unpredictable to human perception. Perhaps most intriguingly, the development of maritime mythology and cultural traditions would evolve without the rich symbolism that tidal cycles have provided to seafaring cultures throughout history. Traditional maritime folklore draws extensively on the relationship between lunar phases, tidal movements, and the mysterious rhythms of ocean life. Without these natural phenomena, maritime cultures might develop different mythological frameworks for understanding their relationship with the sea. The formation of maritime empires and long-distance trade relationships would face different geographic constraints without tidal harbors to provide protected anchorages for large fleets. Many of history's great maritime civilizations developed around natural harbors whose accessibility and protection depend on tidal action. Without these geographic advantages, maritime power might remain more distributed among coastal regions, with different types of natural harbors and anchorages. The mystery of how human understanding of ocean sciences would develop without the obvious laboratory that tidal phenomena provide remains fascinating to consider. Tidal observations have historically provided crucial insights into gravitational forces, celestial mechanics, and fluid dynamics. Without tidal phenomena to study, oceanographic science might develop along different pathways, perhaps focusing more intensively on current patterns, wave mechanics, and marine biology. Perhaps most poetically, the sounds of harbors and coastal waters would lack the distinctive acoustic signatures that tidal action creates. The rush of water through tidal channels, the creaking of boats rising and falling with tide changes, and the rhythmic sounds of waves modified by tidal currents. Maritime soundscapes would speak only in the voices of wind-driven waves and harbor activity, missing the deep tidal bass notes that give coastal waters their familiar music. Only the stars provide navigation references for mariners who must learn to read the sea without the moon's assistance, sailors who venture across waters that never learn to pulse with tidal rhythms, forever challenging but never quite predictable in their movements. In the literary traditions and artistic expressions that might flourish on the moonless world, human creativity would develop without one of its most enduring sources of metaphorical inspiration: The absence of lunar imagery eliminates from human consciousness the vast symbolic vocabulary that moon phases have provided to poets, storytellers, and artists throughout our familiar history. No waxing crescents to represent growth and possibility. No full moons to symbolize completion and illumination. No waning phases to suggest decline and melancholy. The entire emotional and metaphorical landscape of human expression would need to find different celestial territories for its symbolic explorations. The development of romantic poetry and love literature would necessarily draw inspiration from alternative sources without the moon's traditional association with romance, longing, and emotional intimacy. Lovers meeting under starlight rather than moonlight would create different atmospheric associations in literary imagination. The privacy and gentle illumination that moonlight provides for romantic encounters would be replaced by the complete darkness of starlit nights, potentially creating literary traditions that emphasize other senses: sound, touch, scent, over, the visual romance that moonlit scenes typically evoke. Religious and spiritual poetry would evolve different metaphorical frameworks without lunar cycles to represent themes of death and renewal, spiritual transformation, and the eternal rhythms that connect human experience to cosmic patterns. Many mystical traditions on our world use lunar phases as symbols for spiritual development. The dark moon representing spiritual death or introspection, the waxing moon symbolizing growth and learning, the full moon representing enlightenment or spiritual fulfillment. Without these natural symbols, spiritual literature might develop different metaphorical systems based on seasonal changes, stellar patterns, or the rapid day-night cycles of the 6-hour world. The evolution of timekeeping metaphors in literature would develop along entirely different linguistic pathways without monthly rhythms to provide natural units for describing the passage of time. Phrases like "many moons ago" or "once in a blue moon" would never enter human language, eliminated, along with the countless temporal expressions that lunar observations have contributed to human speech. Instead, literary timekeeping might develop around seasonal metaphors, stellar references, or expressions based on the unique 6-hour day cycles of the rapidly rotating world. Children's literature and folklore would necessarily create different narrative structures without the moon's traditional role in bedtime stories, fairy tales, and the gentle nighttime imagery that helps young minds transition from day to sleep. The man in the moon, moonbeams, and lunar creatures that populate children's imagination would never develop, replaced perhaps by star-based characters, constellation stories, or entirely different nighttime mythologies based on the complete darkness that falls each night. Musical traditions would develop different rhythmic and emotional associations without the moon's influence on traditional song structures and lyrical themes. Many folk songs, ballads, and classical compositions draw on lunar imagery for their emotional content and rhythmic patterns. The absence of monthly rhythms might lead to musical traditions more closely tied to daily cycles, seasonal patterns, or the unique acoustic environments that develop in the complete darkness of moonless nights. Visual arts would necessarily explore different symbolic territories without the rich iconographic tradition that lunar imagery has provided to painters, sculptors, and visual artists throughout human history. Landscape paintings would lack the dramatic lighting effects that moonlight creates, potentially leading to artistic traditions that emphasize starlight, aurora phenomena, or the unique visual qualities of rapid dawn and dusk transitions in a 6-hour day. Portraiture and figure studies would develop different approaches to nocturnal scenes and romantic imagery. The development of metaphysical and philosophical literature would proceed without the profound contemplative inspiration that lunar observations have traditionally provided to human thought. The moon's regular phases offer obvious evidence of cyclical time, celestial mechanics, and the relationship between earthly and cosmic rhythms. Without these natural phenomena to contemplate, philosophical traditions might develop different approaches to understanding time, change, and humanity's place in the cosmic order. Perhaps most intriguingly, the development of science fiction and speculative literature would evolve without the Moon as an obvious destination for imaginative space exploration. The lunar surface has provided a natural target for human space travel fantasies throughout literary history, from ancient myths of lunar journeys to modern science fiction. Without a prominent moon to inspire space exploration narratives, speculative fiction might focus more intensively on stellar destinations, alternative planets, or entirely different forms of cosmic adventure. The formation of cultural holidays and festival traditions would develop different seasonal and temporal organizing principles without lunar phases to provide natural celebration timing. Many traditional festivals coordinate their timing with specific lunar phases, using the moon's cycle to organize community celebrations, religious observances, and seasonal festivities. Without lunar calendars, cultural celebrations might synchronize more closely with solar seasons, stellar events, or the unique environmental rhythms of the 6-hour world. The mystery of how human languages would evolve different poetic and metaphorical structures without lunar vocabulary remains fascinating. To consider, the absence of moon-related words might lead to more elaborate stellar vocabularies, more nuanced seasonal terminology, or entirely different ways of describing cyclical time and natural rhythms through linguistic innovation. Perhaps most poetically, the literature of the moonless world would necessarily discover beauty in different celestial phenomena: the slow wheel of constellations across seasons, the rapid succession of abbreviated days and nights, the aurora displays created by the variable magnetic field, or the unique acoustic landscapes that develop in the complete darkness of starlit nights. Human creativity would find its cosmic inspiration in different corners of the sky, creating artistic traditions as rich and emotionally resonant as any lunar-inspired culture, but speaking in entirely different symbolic languages. Only the stars themselves provide the celestial vocabulary for poets who must learn to find romance and mystery in darkness absolute. Writers who create their metaphorical landscapes without the moon's gentle assistance in illuminating the relationship between human experience and cosmic rhythm. Deep within the physiological rhythms of mammalian life on the moonless world, the absence of lunar periodicity would fundamentally alter one of biology's most precisely timed processes: the reproductive cycles that coordinate fertility, ovulation, and population dynamics across countless species. Without the 29-day lunar rhythm that appears to influence menstrual cycles in many mammals, including humans, reproductive timing would necessarily synchronize to entirely different environmental cues, potentially creating biological communities with dramatically altered population dynamics and social structures. The evolution of estrus cycles in mammals would develop along pathways unconstrained by the lunar periodicities that seem to influence reproductive timing in many species on our familiar world. Research suggests that many mammals show reproductive cycles that approximate lunar periods, not just primates, but various ungulates, marine mammals, and even some smaller mammalian species. Without lunar cues, mammalian reproductive cycles might synchronize to seasonal changes, solar rhythms, or the unique 6-hour day-night patterns of the rapidly spinning world, creating reproductive strategies fundamentally different from those we observe. Human reproductive physiology would necessarily develop different temporal organizations without lunar influences on hormonal cycles. While the relationship between lunar phases and human menstrual cycles remains scientifically debated, many women report correlations between their reproductive timing and lunar phases. In the absence of lunar cues, human reproductive cycles might synchronize more closely with seasonal changes, social cues, or environmental factors like temperature and light availability, potentially creating different patterns of fertility and population growth. The social implications of altered reproductive timing extend far beyond individual physiology to affect the fundamental organization of mammalian societies. Many species coordinate their mating activities with lunar phases, ensuring that births occur during optimal environmental conditions or that reproductive activities synchronize across populations to maximize genetic diversity. Without lunar timing, mammalian societies might develop different social structures, perhaps more individualized reproductive strategies or coordination systems based on other environmental cues. Seasonal breeding patterns would face different evolutionary pressures without lunar fine-tuning to optimize reproductive timing within annual cycles. Many mammals use lunar phases to time breeding activities within seasonal windows, ensuring that gestation periods conclude when environmental conditions favor offspring survival. Without lunar cues, seasonal reproduction might become less precisely timed, potentially affecting survival rates and population dynamics in ways that would reshape mammalian ecology. Yet, perhaps most intriguingly, the absence of lunar reproductive rhythms might actually increase mammalian reproductive flexibility and resilience. Without the constraint of coordinating reproductive activities with lunar phases, mammals might evolve more opportunistic breeding strategies that respond directly to environmental conditions, food availability, weather patterns, or social circumstances, rather than following predetermined temporal schedules. The evolution of parental care behaviors would develop different temporal organizations without lunar cues to coordinate birth timing and offspring development. Many mammalian species time their reproductive activities so that births occur during favorable lunar phases, often during dark moon periods when newborns are less visible to predators, or during full moon periods when parents can more easily locate food resources. Without these timing advantages, parental care strategies might evolve different protective and provisioning behaviors. Primate social systems would necessarily develop different hierarchical and competitive structures without the synchronized reproductive cycles that lunar phases typically create in many species. Research on various primate communities suggests that female reproductive cycles often synchronize with lunar periods, creating predictable patterns of social interaction, male competition, and group dynamics. Without lunar synchronization, primate societies might develop more individually variable social patterns. The development of human cultural institutions around reproduction and fertility would evolve without the symbolic and practical frameworks that lunar cycles have traditionally provided. Many human cultures have developed elaborate ritual and social systems that coordinate with lunar phases, timing marriages, fertility ceremonies, and birth-related observances with specific moon phases. Without lunar references, human reproductive culture might organize around seasonal festivals, agricultural cycles, or entirely different temporal frameworks. Perhaps most mysteriously, the absence of lunar reproductive rhythms might affect the evolution of consciousness and cognitive development in ways that remain purely speculative. Some researchers have suggested that lunar influences on reproductive hormones might also affect neural development, cognitive cycles, and even dream patterns. If lunar rhythms do influence brain development and function, their absence might lead to the evolution of nervous systems with different cognitive architectures and capabilities. The population dynamics of mammalian communities would operate under different mathematical models without the regular reproductive pulses that lunar coordination typically creates. Synchronized reproduction often creates population waves that affect predator-prey relationships, resource competition, and ecological stability. Without lunar synchronization, mammalian populations might show more continuous but less dramatic fluctuations, potentially creating more stable but less resilient ecological relationships. The mystery of how mammalian migration patterns would develop without lunar timing cues for reproductive activities remains fascinating to consider. Many species coordinate long-distance migrations with reproductive cycles, timing their movements to arrive at breeding grounds during optimal lunar phases. Without these timing cues, migration patterns might synchronize with different environmental indicators or develop more flexible, individually variable timing strategies. Perhaps most poetically, the absence of lunar reproductive rhythms would eliminate one of biology's most elegant examples of cosmic influence on terrestrial life. The coordination between celestial mechanics and mammalian physiology represents a profound connection between astronomical and biological time that speaks to the deep integration of earthly life with cosmic rhythms. Without these connections, mammalian reproduction would operate as a purely terrestrial phenomenon, unconnected to the larger rhythms of the solar system. Only the slow wheel of seasons provides temporal organization for reproductive cycles that must learn to keep time. Without the moon's ancient influence, mammalian communities that synchronize their most intimate biological rhythms to earth-bound rather than celestial cues. In the astronomical observations of civilizations that might arise on the moonless world, one of the most profound and scientifically transformative phenomena would remain forever absent from human experience. Solar eclipses, those rare and magnificent events where the moon passes directly between Earth and Sun, temporarily blocking our star's brilliant face, would never darken the skies of the moonless world. The absence of these cosmic alignments eliminates from human consciousness the natural laboratory that eclipses have provided for advancing understanding of stellar physics, atmospheric science, and the fundamental nature of celestial mechanics. The development of early astronomy would follow entirely different pathways without the dramatic evidence that solar eclipses provide for the reality of celestial motion and orbital mechanics. Ancient astronomers normally gain crucial insights into the three-dimensional nature of space from eclipse observations, the way celestial bodies can pass in front of each other, casting shadows and revealing their relative positions in ways that transform abstract astronomical theory into visible, undeniable reality. Without eclipses, early astronomical understanding might develop more slowly and along more purely mathematical rather than observational lines. Solar physics would face unprecedented research limitations without the unique experimental conditions that total solar eclipses create. During eclipse totality on our world, the moon blocks the sun's brilliant photosphere, revealing the normally invisible solar corona and allowing detailed study of stellar atmospheric structure, magnetic field, dynamics, and solar wind formation. These observations have provided fundamental insights into stellar physics that would remain largely inaccessible to civilizations developing on the moonless world, potentially delaying discoveries about stellar evolution and the nature of stars themselves. The historical development of relativity theory and gravitational physics would lack one of its most elegant experimental confirmations without solar eclipses to provide natural laboratories for testing theoretical predictions. Einstein's theory of general relativity received crucial observational support from eclipse expeditions that measured the gravitational bending of starlight around the sun, observations possible only during the few minutes of totality when stars become visible near the solar limb. Without eclipse opportunities, theoretical physics might develop different experimental approaches for testing gravitational theories. Navigation and timekeeping systems would develop without the precise astronomical references that eclipse predictions normally provide. Ancient civilizations used eclipse cycles to develop accurate calendar systems, demonstrate the predictive power of astronomical calculation, and establish precise temporal references for historical record-keeping. The Saros cycle, the 18-year, 11-day period that governs eclipse repetition, has provided one of humanity's most reliable tools for long-term astronomical prediction and calendar coordination. Yet, perhaps most profoundly, human, psychological, and cultural development would proceed without the transformative experience that witnessing total solar eclipses provides. These events create psychological impacts that transcend simple astronomical observation. The sudden darkness during daylight, the dramatic temperature drop, the visible stars in the middle of the day, and the ethereal beauty of the solar corona. create experiences that have influenced human spiritual and philosophical development throughout history. Without these profound cosmic encounters, human consciousness might develop different relationships with astronomical phenomena. The formation of scientific institutions and research methodologies would lack the historical precedent that eclipse expeditions have provided for international scientific cooperation. Many of history's most important eclipse observations required coordinated efforts by scientists from multiple countries, establishing patterns of international collaboration that influence the development of scientific institutions. Eclipse research has historically demonstrated the value of precise measurement, careful observation, and collaborative data analysis that forms the foundation of modern scientific methodology. Religious and philosophical systems would develop. Without the powerful natural symbols that solar eclipses have provided throughout human history. These events have traditionally been interpreted as cosmic omens, divine interventions, or profound spiritual experiences that connect human consciousness with larger cosmic patterns. The absence of eclipses might lead to spiritual traditions that find their cosmic connections through other astronomical phenomena, perhaps aurora displays, meteor showers, or the unique rapid day-night cycles of the 6-hour world. The development of optical instruments and precision measurement techniques would follow different historical pathways without the demanding observational requirements that eclipse research has traditionally imposed. Eclipse observations require extremely precise timing, sophisticated optical systems, and innovative measurement techniques that have driven advances in instrument design and manufacturing. Without these research pressures, technological development might proceed along different trajectories. Perhaps most intriguingly, the study of atmospheric physics and climate science would lack the unique experimental conditions that eclipses create for understanding how sudden changes in solar radiation affect atmospheric dynamics. Eclipse observations provide natural experiments in rapid atmospheric cooling, allowing researchers to study how quickly and dramatically atmospheric conditions respond to changes in solar heating. These insights have contributed to understanding of climate sensitivity and atmospheric response times. The mystery of how human understanding of cosmic scale and celestial mechanics would develop without the vivid demonstrations that eclipses provide remains fascinating to consider. These events offer unmistakable evidence that celestial bodies exist at different distances from Earth, move in predictable patterns, and interact through gravitational forces. Without eclipses, astronomical education might require more abstract, mathematical approaches to convey concepts that eclipse observations make immediately apparent. Perhaps most poetically, the skies of the moonless world would never experience the profound silence that accompanies totality, the moment when birds stop singing, temperatures drop, and the entire natural world responds to the sudden onset of artificial night during daylight hours. The acoustic signature of eclipses, as much as their visual impact, creates experiences that connect human consciousness with the reality of our planet's movement through space. Only the unobscured sun provides illumination for astronomers who must learn to study stellar physics without the natural laboratory that eclipses provide. Scientists who develop their understanding of cosmic mechanics without witnessing the shadow play that demonstrates so elegantly how celestial bodies dance through space around our lonely, moonless world. In the deepening twilight hours of the moonless world, when the 6-hour day surrenders to its brief night, human consciousness would confront a cosmic solitude unknown to any civilization that has ever gazed upward at a companion world hanging in the darkness. The night sky above this lonely planet stretches empty of any prominent celestial companion. No pale disk to cast shadows, no waxing and waning presence to mark the passage of months, no bright neighbor to remind earthbound observers that worlds can exist beyond the immediate terrestrial realm. The psychological impact of such cosmic isolation would permeate every aspect of human experience, from individual contemplation to collective understanding of humanity's place in the universe. The development of human spatial awareness would Proceed without the profound three-dimensional reference point that a visible moon normally provides. Children growing up under moonless skies would develop different intuitive understandings of distance, scale, and the reality of worlds beyond Earth. The moon serves as humanity's first lesson in cosmic perspective, a clearly spherical world, visibly three-dimensional, obviously separate from Earth yet gravitationally connected. Without this celestial teacher, human spatial imagination might remain more earth-bound, developing cosmic awareness only through the distant points of starlight that provide less obvious evidence of the universe's three-dimensional nature. Philosophical. Traditions would necessarily grapple with different fundamental questions about existence and cosmic purpose without the moon's example of orbital companionship. Many human philosophical systems have drawn inspiration from the moon's regular presence, its constancy despite change, its independence yet connection to Earth, its role as witness to human history. The absence of any prominent celestial companion might lead to philosophical traditions that emphasize either cosmic isolation or the unique specialness of Earth as the only visible world in the immediate universe. The development of human curiosity about space exploration would face different, motivational landscapes without an obvious nearby destination for imaginative space travel. The moon has served throughout human history as the most accessible target for space exploration fantasies, close enough to seem reachable, visible enough to inspire detailed speculation about its surface and composition. Without this nearby world to capture human imagination, space exploration dreams might focus more immediately on the distant stars, potentially creating more ambitious but less achievable goals for spacefaring civilizations. Romantic and emotional relationships would develop different symbolic associations without the moon's traditional role in human courtship and intimate connection. Lovers throughout history have shared the experience of gazing at the same moon, using its presence as a symbol of connection across distance and time. The phrase "lover's moon" captures the way this celestial companion has served as witness and participant in human emotional life. Without lunar romanticism, human courtship might develop different celestial associations or focus more intensively on terrestrial beauty and shared earthly experiences. The psychology of nighttime contemplation would develop along different pathways. Without the moon's gentle illumination to soften the transition from day to absolute darkness, moonlight provides enough illumination to maintain spatial orientation and environmental awareness while encouraging introspective thought. The complete darkness of moonless nights might create more intense introspective experiences, potentially leading to different approaches to meditation, contemplation, and the quiet mental activities that typically occur during nighttime hours. Perhaps, most profoundly, the absence of any visible celestial companion would affect human understanding of loneliness and companionship at the deepest psychological levels. The moon serves as a cosmic companion that is always present yet always distant, providing a model for relationships that maintain connection across space and time. Without this celestial example, human concepts of companionship might develop different characteristics, perhaps emphasizing either more immediate physical connection or more abstract spiritual bonds. The development of navigation and wayfinding would necessarily create different relationships between human spatial awareness and cosmic orientation. Many traditional navigation systems use the moon's position and phase as references for determining direction and time during travel. Without lunar navigation aids, human spatial orientation would depend more heavily on stellar patterns, creating navigation systems that require more extensive astronomical knowledge but potentially develop more sophisticated star-reading capabilities. Cultural concepts of cycles and renewal would develop without the moon's powerful example of regular death and rebirth through its phases. Many human cultures use lunar cycles as metaphors for life, death, and renewal, the way the moon disappears completely during new moon phases yet returns with predictable regularity. Without these natural cycles, human understanding of renewal, and regeneration might draw inspiration from seasonal changes, creating cultural traditions more closely tied to terrestrial rather than celestial rhythms. The formation of human concepts about cosmic scale and astronomical distance would proceed without the Moon's role as an intermediate reference point between Earth and the stars. The Moon provides an obvious example of a world that is clearly separate from Earth, yet obviously much closer than the stars. Without this intermediate cosmic distance marker, human understanding of cosmic scale might develop more slowly, potentially leading to longer periods of confusion about whether stars and planets exist at similar or vastly different distances from Earth. The mystery of how human consciousness would adapt to complete cosmic solitude remains one of the most intriguing aspects of moonless evolution. The psychological comfort that comes from having a celestial companion, even a distant, unreachable one, might play important roles in human mental development and emotional resilience. The absence of any prominent celestial neighbor might create either more self-reliant human psychology or deeper feelings of cosmic loneliness that would influence art, philosophy, and spiritual development. Perhaps most poetically, the humans of the moonless world would never experience the particular form of cosmic humility that comes from contemplating another world hanging in space. The way the Moon's visible presence reminds observers that Earth itself is a world among worlds, a planet moving through space rather than the fixed center of a universe that revolves around human experience. This fundamental shift in cosmic perspective might delay or alter the development of scientific worldviews that recognize Earth's place as one world among many in a vast universe. Only the distant stars provide celestial company for a species that must learn to find cosmic meaning in the remote points of light that wheel overhead without offering any nearby companion to share the long journey through space and time. Along the static shores of the moonless world, where restless waves meet unmoved beaches, there exists a silence that would seem profound beyond measure to any observer familiar with the rhythmic breathing of tidal coastlines. The absence of that ancient sound, the whisper of waters rising and falling with lunar pull, creates shorelines that speak only in the immediate vocabulary of wind and weather, never learning the deeper grammar of gravitational conversation between worlds. Here, the eternal dialogue between celestial mechanics and terrestrial waters remains forever unspoken, leaving coastlines that know only the present tense of wave action, never the perfect conditional of what might rise or fall with cosmic timing. The beaches hold their positions with geological stubbornness, neither gaining nor losing sand through the regular transport mechanisms that tidal currents typically provide. Sediments settle where wind and rivers place them, remaining undisturbed by the twice-daily rearrangement that normally sculpts coastal topography into the familiar forms of our tidal world. Rocky shores maintain their configurations across centuries, unmarked by the high-water stains and barnacle lines that usually record the vertical reach of oceanic ambition. The very stones seem to listen for voices that will never call their names, waiting for rhythms that will never disturb their ancient rest. In tidal pools that never were, the chemistry of life follows pathways constrained by dilution and dispersion, rather than the concentration and mixing that tidal action typically provides. Organic molecules dissolved in these static shallows remain at the concentrations that currents and diffusion create, never experiencing the evolutionary pressure cooker of repeated evaporation and renewal that drives complex biochemistry toward the threshold of living systems. The building blocks of life drift in permanent solution, like ingredients for recipes that will never be written, waiting for mixing patterns that will never stir their molecular potential into the complex arrangements that define biology. The soundscape of these tideless margins lacks the percussion section that tidal action normally provides to coastal music. No rhythmic rush of water through narrow channels, no gentle lapping of rising seas against stone, no soft withdrawal of receding waves dragging sand and pebbles back toward deeper waters. The acoustic signature of these shores speaks only in the immediate present tense of wind-driven waves, missing the past and future tenses that tidal sounds typically add to coastal conversation. The beaches speak, but only in monosyllables: crash, hiss, repeat, never learning the complex sentences that tidal grammar typically teaches to the interface between land and sea. Marine organisms attempting to establish communities along these. Static margins encounter environmental conditions that remain locked in singular states rather than oscillating through the dual personalities that tidal zones typically display. Creatures that might have evolved amphibious capabilities instead remain fully aquatic or fully terrestrial, never experiencing the evolutionary pressure that creates organisms capable of surviving in both conditions simultaneously. The biological communities that develop here know only one set of environmental rules at a time, never learning the flexibility that comes from regular practice at being both submerged and exposed, both marine and terrestrial, both today and tomorrow. The geological record accumulates differently along these unchanging shores, where sedimentary layers form through processes uncomplicated by the rhythmic reworking that tidal action typically imposes. Rock strata develop with simpler stories to tell, tales of seasonal storm patterns, river flood cycles, and the slow accumulation of wind-blown materials, but never the complex narratives written in alternating layers that record the twice-daily breathing of tidal shores. These sediments preserve history in single voice rather than the call and response patterns that tidal deposits typically create, leaving geological archives that speak in monotone rather than the varied inflections of rocks that remember oceanic. Conversations. Navigation along these coasts develops without the reliable timing references that tidal predictions typically provide to maritime cultures. Harbors that never change their depth offer consistent but limited access, never opening deeper channels during high tides or revealing hidden obstacles during low tides. The relationship between coastal peoples and their seas remains simplified, lacking the complex scheduling and timing considerations that tidal cultures typically develop. Maritime activities proceed according to weather and season, but never according to the more intimate calendar that lunar gravity typically writes in water levels and current flows. The very concept of harbor design evolves along different principles, when coastal engineers never need to accommodate the vertical range of water levels that tidal harbors typically require. Docks and piers maintain constant relationships with water surfaces, never rising and falling with oceanic breathing, never requiring the flexible connections and adjustable structures that tidal engineering typically demands. Coastal architecture speaks a simpler structural language, expressing only the present indicative mood of wave action, rather than the subjunctive possibilities that tidal ranges typically introduce to waterfront construction. Perhaps most poetically, the absence of tides eliminates from human experience one of the most reliable examples of cosmic influence on earthly affairs. The regular rise and fall of oceanic levels provides obvious daily evidence that celestial mechanics reach down to touch terrestrial experience in ways that affect practical human activities. Without tidal demonstrations of gravitational influence, the connection between astronomical theory and earthly experience becomes more abstract, potentially delaying human understanding of the ways that cosmic forces shape daily life on planetary surfaces. The mystery of what forms of beauty might develop along these static shores remains purely speculative. Perhaps the unchanging relationship between water and land creates different aesthetic possibilities, coastlines of perfect consistency where the interface between sea and shore maintains ideal proportions across seasons and centuries. Or, perhaps, the absence of tidal variation creates monotonous repetition that lacks the dynamic beauty that comes from regular transformation and renewal. Only the wind remains to stir these motionless margins, to provide the mixing and movement that gravity typically contributes to the boundary zones between terrestrial and marine worlds. The waves continue their ancient work of shaping stone and moving sand, but they labor without the assistance of those twice-daily partners that usually help sculpt coastlines into the complex, productive, ever-changing interfaces that make the edges of continents into cradles of evolutionary possibility. The silence where tides should sound becomes itself a presence, an absence so profound that it transforms the very nature of what it means for water to meet land on a world that never learned to breathe with lunar rhythms, never discovered the cosmic choreography that teaches oceans to dance with gravitational music played by celestial partners invisible in the darkness overhead. In the deep oceanic trenches and abyssal plains of the moonless world, the absence of tidal mixing creates underwater environments that would astonish any marine biologist familiar with the dynamic deep-sea ecosystems of our tidally influenced Earth. These profound depths, normally stirred by the subtle but persistent effects of tidal currents that penetrate even to the deepest oceanic basins, instead lie in states of chemical and physical stratification unknown in any familiar marine environment. The deep waters accumulate dissolved nutrients, trace metals, and organic compounds in concentrations that remain undisturbed for millennia, creating underwater provinces as chemically distinct as separate atmospheric layers. The formation of deep water masses proceeds along entirely different pathways without tidal mixing to transport and blend waters of different origins. Cold, dense water that forms at polar surfaces and sinks to abyssal depths remains isolated in its basin of formation, carrying the chemical signature of its polar origins unchanged across geological timescales. These deep water masses become archives of ancient climate conditions, preserving dissolved oxygen isotope ratios, carbon signatures, and trace element concentrations that record environmental conditions from the time of their formation centuries or millennia earlier. Hydrothermal vent communities, those remarkable deep-sea oases that support unique ecosystems around underwater volcanic activity, would develop under fundamentally different chemical regimes without tidal mixing to disperse and dilute their mineral-rich emissions. The hot, chemically laden water that emerges from seafloor vents would create more concentrated and persistent chemical plumes, potentially supporting larger and more diverse chemosynthetic communities, but also creating toxic zones that might inhibit colonization by organisms adapted to more dilute chemical environments. Deep-sea sediment transport operates through mechanisms uncomplicated by the tidal currents that normally contribute to the reworking and redistribution of seafloor deposits. Sediments accumulate primarily through the slow rain of organic matter and mineral particles from surface waters, settling into layers that preserve more complete records of surface productivity and climate history. Without tidal disturbance, these sedimentary archives maintain higher resolution records of environmental change, creating underwater libraries of planetary history with unprecedented temporal detail. The vertical migration patterns that characterize many deep-sea organisms would develop without the tidal timing cues that normally help coordinate these daily movements between surface and deep waters. Many marine organisms undertake regular vertical migrations to feed in productive surface waters during night hours, while sheltering in deeper waters during daylight. But without tidal rhythms to provide additional timing coordination, these migration patterns might become less synchronized across populations, potentially reducing the efficiency of this vertical resource transport system. Yet, perhaps most profoundly, the absence of deep tidal mixing eliminates one of the primary mechanisms that maintains global ocean circulation patterns. The thermohaline circulation, that global conveyor belt of currents that transports heat, nutrients, and dissolved gases around the planet, depends partly on tidal mixing to maintain the density gradients that drive deep water formation and circulation. Without tidal contribution to this mixing, global ocean circulation might operate at reduced efficiency, potentially affecting climate regulation and marine productivity on planetary scales. Abyssal benthic communities, those sparse but specialized organisms that inhabit the deepest ocean floors, would encounter environmental conditions of remarkable stability without the subtle tidal influences that normally create small but measurable variations in current flow, temperature, and chemical composition even at the greatest depths. These communities might evolve along more specialized evolutionary pathways, adapted to extremely consistent environmental conditions, but potentially less resilient to environmental changes when they do occur. The formation of oxygen minimum zones, those layers of deep water where dissolved oxygen concentrations become too low to support most marine life, would develop different characteristics without tidal mixing to enhance vertical oxygen transport. These zones might become more pronounced and persistent, creating underwater deserts that could expand or contract over geological timescales based on changes in surface productivity and deep water formation rates rather than the more dynamic patterns that tidal mixing normally creates. Deep-sea mining operations, should they develop on the moonless world, would encounter seafloor conditions of unusual chemical concentration and stability. Mineral deposits formed through hydrothermal activity or sedimentary processes would accumulate without the dispersive effects of tidal currents, potentially creating more concentrated ore bodies but also more persistent environmental impacts from extraction activities. The mystery of how deep-sea biodiversity would develop without the subtle but persistent environmental variations that tidal mixing typically provides remains largely theoretical. Some marine biologists speculate that the stable conditions of tideless deep waters might actually support higher biodiversity by eliminating environmental stresses, while others suggest that the lack of environmental variation might reduce evolutionary pressure for adaptation and speciation. Perhaps most mysteriously, the deep waters of the moonless world would develop acoustic properties unlike any familiar oceanic environment. Sound transmission through these chemically stratified waters would follow different pathways, potentially creating underwater acoustic environments where sounds travel along distinct chemical boundaries rather than mixing uniformly through the water column. Deep-sea organisms that rely on acoustic communication might evolve different strategies adapted to these stratified sound transmission characteristics. The irony of these stable deep waters lies in their potential for preserving more complete records of planetary environmental history while simultaneously supporting ecosystems that might be less resilient to environmental change. The chemical archives preserved in undisturbed deep waters could provide unprecedented insights into climate history, but the organisms adapted to such stable conditions might be more vulnerable to disruption when environmental changes do occur. Only the patient accumulation of sediments and the slow chemistry of dissolved compounds mark the passage of time in these undisturbed depths, abyssal realms that never learned the subtle breathing that tidal mixing typically brings to even the deepest oceanic basins, forever stable in their chemical memories of ancient seas. Beneath the rapidly spinning surface of the moonless world, the planet's interior dynamics operate under thermal and mechanical conditions that would fundamentally alter the processes of mountain building, volcanism, and continental drift. The absence of tidal flexing, those subtle but persistent gravitational stresses that the Moon normally imposes on Earth's solid body, eliminates a significant source of internal heating and mechanical deformation that typically contributes to geological activity. Without the Moon's gravitational massage working continuously on the planet's interior, the patterns of heat flow, magma generation, and tectonic motion would develop along pathways unknown to any geologically active world in our familiar solar system. The generation of internal heat through tidal friction, normally a minor but measurable contributor to planetary thermal budgets, disappears entirely from the moonless world's energy balance. This elimination of tidal heating affects the temperature gradients within the mantle, potentially altering the efficiency of convective heat transport that drives plate tectonics and volcanic activity. Computer models of planetary thermal evolution suggest that the absence of tidal heating might reduce overall geological activity by small but cumulative amounts over geological time scales, potentially creating a world that remains tectonically active longer but with reduced intensity. Earthquake patterns would develop different characteristics without the additional stress loading that tidal forces normally impose on fault systems. Seismologists studying earthquake-triggering mechanisms have identified correlations between tidal stress cycles and the timing of seismic events, particularly for faults that are close to failure thresholds. Without tidal stress modulation, earthquake occurrence might become more irregular and harder to predict, lacking the subtle periodicities that tidal influences sometimes impose on seismic activity patterns. The formation of ore deposits and mineral concentrations would proceed, without the mechanical and thermal effects that tidal deformation typically contributes to geological processes. Hydrothermal systems that concentrate metals and create valuable mineral deposits operate partly through fracture patterns and fluid flow pathways that can be influenced by tidal stress cycles. Without these mechanical influences, ore formation might follow different pathways, potentially creating different types of mineral deposits or altering the efficiency of concentration processes that create economically viable ore bodies. Volcanic activity patterns would develop without the subtle triggering effects that tidal stresses sometimes provide to magma chambers approaching eruption thresholds. Studies of volcanic eruption timing have identified statistical correlations between tidal cycles and eruption occurrence for some volcano types, particularly those with magma chambers under high pressure. Without tidal triggering, volcanic eruptions might occur with different timing patterns, potentially affecting the predictability of volcanic hazards and the development of early warning systems. Yet, perhaps most intriguingly, the absence of tidal flexing might actually contribute to more stable geological conditions in some respects. The continuous mechanical stress that tidal forces impose on planetary interiors can contribute to fracturing, fault development, and the weakening of crustal materials over geological time. Without this persistent mechanical influence, some geological structures might develop greater long-term stability, potentially creating more durable mountain ranges and more stable continental configurations. The development of geothermal energy. Systems would encounter different subsurface thermal conditions without the contribution of tidal heating to local temperature gradients. Geothermal power generation depends on accessing underground heat sources, and the absence of tidal heating might reduce the availability of shallow geothermal resources while potentially preserving deeper heat sources for longer periods. The distribution of geothermal energy potential might follow different geographic patterns than familiar worlds with tidal heating contributions. Crustal flexure patterns, the way that continental plates bend and deform under various loads, would operate without the additional stress components that tidal forces normally contribute to large-scale deformation processes. The loading of continental shelves by ice sheets during glacial periods, the depression of landmasses under large lakes or seas, and the rebound of crust after load removal would proceed with different mechanical characteristics in the absence of background tidal stresses. The formation of petroleum and natural gas deposits would develop without the subtle but persistent pressure variations that tidal effects sometimes contribute to sedimentary basin dynamics. Hydrocarbon generation and migration depend partly on pressure and temperature conditions within sedimentary sequences, and the absence of tidal influences might alter the timing and efficiency of these processes, potentially affecting the distribution and quality of fossil fuel resources. Perhaps most mysteriously, the long-term evolution of planetary magnetic field generation might proceed along different pathways without the mechanical effects that tidal forces exert on the planet's interior structure. The convective processes in the outer core that generate Earth's magnetic field operate through complex interactions between thermal and mechanical forces, and the absence of tidal contributions to core dynamics might influence magnetic field strength, stability, and reversal patterns over geological timescales. The geological record preserved in rock formations would lack the subtle periodicities that tidal influences sometimes impose on sedimentary and igneous processes. Some sedimentary sequences show layering patterns that correlate with tidal cycles, while certain volcanic deposits preserve evidence of tidal triggering effects. Without these influences, geological records might preserve different types of information about planetary environmental history and internal dynamics. The irony of reduced tidal influence on geological processes becomes apparent when considering that a more tectonically stable world might actually be less favorable for life in the long term. Geological activity helps regulate planetary climate through volcanic outgassing, maintains the recycling of nutrients through rock weathering and erosion, and creates the topographic diversity that supports biological diversity. A world with reduced geological activity might become more environmentally stable but less capable of long-term climate regulation. Only the deeper, more fundamental forces of radioactive decay and primordial heat drive the geological engines of the moonless world, planetary dynamics that operate without the subtle but persistent assistance of tidal energy, forever more dependent on internal heat sources and less connected to the gravitational rhythms that typically link planetary geology to celestial mechanics. In the stratosphere and upper atmospheric layers of the moonless world, the absence of subtle gravitational influences creates circulation patterns and chemical compositions that would intrigue any atmospheric scientist familiar with the complex dynamics of our moon-influenced atmosphere. Without the slight but measurable atmospheric tides that lunar gravity normally generates, those twice-daily pressure oscillations that propagate through the entire atmospheric column, the upper atmosphere develops circulation patterns driven solely by solar heating, planetary rotation, and chemical processes, creating meteorological conditions unknown to any world that experiences regular gravitational atmospheric pumping. The formation of atmospheric layers proceeds without the mixing effects that lunar atmospheric tides typically contribute to vertical transport processes. These gravitational atmospheric tides, distinct from oceanic tides but following similar principles, normally create subtle but persistent vertical motions that help transport trace gases, aerosols, and energy between different atmospheric levels. Without this mixing mechanism, atmospheric layers become more chemically distinct and physically isolated, potentially creating stratification patterns that persist for longer periods and resist the vertical exchange processes that normally characterize atmospheric dynamics. Ozone formation and destruction cycles in the upper atmosphere would operate under different chemical regimes without the pressure variations that lunar atmospheric tides typically create. The delicate balance of photochemical reactions that maintain stratospheric ozone concentrations depends partly on pressure and temperature conditions that can be influenced by atmospheric tidal oscillations. Without these regular pressure variations, ozone chemistry might proceed along different pathways, potentially affecting the efficiency of ultraviolet radiation absorption and the protection of surface environments from harmful solar radiation. Weather. Pattern formation in the lower atmosphere would develop without the subtle but measurable influences that lunar atmospheric tides sometimes impose on pressure gradient development and wind circulation patterns. Meteorologists studying atmospheric dynamics have identified correlations between lunar phases and certain weather pattern characteristics, particularly in the timing and intensity of cyclonic systems. Without these influences, weather forecasting might become slightly less complex but also might lose some of the subtle periodicities that help improve long-term meteorological predictions. The development of jet stream patterns, those high-altitude rivers of fast-moving air that influence weather systems across entire continents, would operate without the additional forcing mechanisms that atmospheric tides typically contribute to upper atmospheric circulation. Jet streams form through complex interactions between temperature gradients, planetary rotation, and pressure differences, and the absence of tidal atmospheric oscillations might create more stable but potentially less dynamic upper atmospheric circulation patterns. Yet, perhaps most intriguingly, the absence of atmospheric tides might actually contribute to more predictable long-term atmospheric behavior in some respects. The regular oscillations that lunar gravitational influences impose on atmospheric pressure and circulation can contribute to complex feedback loops and nonlinear atmospheric responses that make weather prediction more challenging over extended time periods. Without these additional variables, atmospheric modeling might achieve greater accuracy for certain types of long-term forecasting. Radio wave propagation through the upper atmosphere would encounter different ionospheric conditions. Without the regular variations in electron density that atmospheric tides typically create, the ionosphere, that electrically charged layer of the upper atmosphere that reflects radio signals and enables long-distance communication, develops its charge density patterns partly through process that can be influenced by atmospheric tidal oscillations. Without these variations, radio communication systems might experience more consistent but potentially less optimal propagation conditions. Aurora formation patterns would develop under different magnetospheric atmospheric interaction conditions without the atmospheric density variations that tidal oscillations typically create in the upper atmosphere. The interaction between incoming charged particles from space and atmospheric gases that creates auroral displays depends partly on atmospheric density distributions that can be influenced by atmospheric tidal effects. Without these variations, auroral patterns might become more geographically stable but potentially less dynamic in their temporal characteristics. Atmospheric chemistry related to pollution transport and dispersion would operate without the vertical mixing contributions that atmospheric tides typically provide. Industrial emissions, volcanic gases, and other atmospheric pollutants are normally dispersed partly through tidal atmospheric mixing processes that help transport contaminants between different atmospheric layers. Without this mixing mechanism, atmospheric pollution might remain more concentrated in specific layers, potentially creating different environmental health challenges and air quality patterns. The development of atmospheric escape processes. The mechanisms by which planetary atmospheres gradually lose material to space would proceed without the additional energy transport that atmospheric tides typically contribute to upper atmospheric heating. Atmospheric escape rates depend partly on temperature and energy conditions in the upper atmosphere that can be influenced by tidal heating effects. Without these contributions, atmospheric loss rates might proceed at different rates, potentially affecting the long-term evolution of atmospheric composition and density. Perhaps most mysteriously, the absence of atmospheric tides might affect the development of complex atmospheric resonance phenomena that sometimes occur when tidal oscillations interact with natural atmospheric wave patterns. These resonance effects can amplify or dampen atmospheric oscillations in ways that influence weather pattern development and atmospheric stability. Without tidal contributions to these resonance systems, atmospheric dynamics might develop different types of oscillatory behavior based entirely on solar and rotational forcing. Seasonal atmospheric patterns would develop without the subtle modulations that atmospheric tidal cycles typically impose on the relationship between solar heating and atmospheric response. The interaction between seasonal solar heating variations and atmospheric tidal oscillations can create complex seasonal atmospheric behaviors that influence climate patterns and weather system development. Without tidal modulation, seasonal atmospheric transitions might become more directly related to solar heating patterns, but potentially less complex in their temporal characteristics. The irony of simplified atmospheric dynamics becomes apparent when considering that the absence of atmospheric tides might actually make the atmosphere less efficient at certain types of energy and material transport between atmospheric layers. While the elimination of tidal complexity might make atmospheric modeling more straightforward, it might also reduce the atmospheric system's ability to respond flexibly to environmental changes and maintain optimal compositions for supporting surface life. Only the direct forces of solar heating and planetary rotation drive the atmospheric circulation of the moonless world, creating meteorological patterns that operate without the subtle but persistent assistance of gravitational atmospheric pumping, forever more dependent on thermal and rotational forces and less connected to the gravitational rhythms that typically help mix and energize planetary atmospheres. In the evolutionary pathways of intelligence and consciousness that might eventually arise on the moonless world, the absence of lunar rhythms would fundamentally alter the neural architectures and cognitive patterns that characterize complex thinking systems. Without the regular environmental periodicity that lunar cycles typically provide to developing nervous systems, the brains that evolve on this world would necessarily organize their temporal processing, memory formation, and consciousness patterns around entirely different rhythmic frameworks, perhaps the rapid 6-hour day-night cycles, the chaotic obliquity variations, or purely internal biological oscillations that develop independently of external celestial cues. The formation of circadian timing systems in neural tissue would proceed without the intermediate temporal framework that lunar periodicity normally provides between daily and seasonal rhythms. Neuroscientists studying biological clocks have identified lunar-related oscillations in brain activity patterns, hormone production cycles, and sleep-wake rhythms that appear to influence cognitive performance and emotional regulation. Without these lunar neural rhythms, brain development might follow pathways that create either more rigid daily timing systems or more flexible temporal processing capabilities that operate independently of any regular environmental periodicity. Memory, consolidation, processes, those crucial neural mechanisms that transfer information from temporary to permanent storage, would develop without the monthly rhythmic frameworks that lunar cycles might normally provide to memory formation. Some research suggests that lunar periodicities influence sleep patterns and dream cycles in ways that affect memory processing and learning efficiency. Without lunar memory rhythms, neural systems might develop alternative temporal frameworks for organizing memory consolidation, perhaps creating more continuous but less cyclically organized approaches to information storage and retrieval. The development of social intelligence and group coordination abilities would proceed without the shared temporal references that lunar cycles typically provide to social coordination. Many social species use lunar timing cues to coordinate group activities, mating behaviors, and seasonal migrations in ways that require complex social intelligence and communication capabilities. Without lunar social rhythms, intelligent species might develop more individually variable social timing systems or more sophisticated communication methods for coordinating group activities without shared celestial timing references. Language. Evolution would necessarily develop different temporal vocabulary and conceptual frameworks without the monthly periodicity that lunar observations typically contribute to human linguistic development. The absence of lunar-related words and concepts would eliminate entire categories of temporal expression, potentially leading to languages that organize time concepts around seasonal variations, stellar patterns, or the unique 6-hour day cycles of the rapidly spinning world. Temporal metaphors and abstract thinking patterns might develop along entirely different conceptual pathways. Yet, perhaps most profoundly, the evolution of mathematical and scientific thinking would proceed without the regular periodicity demonstrations that lunar cycles typically provide to developing intelligence. Lunar phases offer obvious examples of cyclical patterns, predictable change sequences, and the relationship between observation and mathematical prediction that historically have influenced the development of scientific thinking. Without lunar mathematical models, intelligence might develop different approaches to understanding pattern recognition, prediction systems, and the relationship between mathematical theory and observable phenomena. Artistic and creative intelligence would necessarily find inspiration in different rhythmic and aesthetic territories without the rich symbolic and emotional associations that lunar imagery typically provides to creative consciousness. The development of poetry, music, visual arts, and storytelling would proceed along pathways that draw inspiration from stellar patterns, seasonal changes, or the unique environmental characteristics of the moonless world, potentially creating artistic traditions with entirely different emotional and aesthetic foundations. The formation of religious and philosophical consciousness would develop different conceptual frameworks for understanding cosmic relationships, and spiritual meaning without the lunar symbolism that typically influences metaphysical thinking. Many philosophical and religious traditions use lunar cycles as metaphors for spiritual development, cosmic order, and the relationship between individual consciousness and universal patterns. Without lunar philosophical models, spiritual intelligence might develop different approaches to understanding cosmic meaning and individual purpose. Navigation intelligence, the cognitive capabilities required for spatial orientation and long-distance travel, would develop without the reliable celestial references that lunar observations typically provide to wayfinding systems. The evolution of spatial intelligence might follow pathways that emphasize stellar pattern recognition, environmental landmark memory, or entirely different approaches to spatial navigation that operate independently of celestial timing references. Perhaps most mysteriously, the development of consciousness and self-awareness might proceed along different pathways without the temporal stability and rhythmic predictability that lunar cycles typically provide to developing neural systems. Some theories of consciousness suggest that regular environmental rhythms contribute to the formation of stable temporal frameworks that support complex self-awareness and abstract thinking capabilities. Without lunar consciousness rhythms, self-aware intelligence might develop different temporal characteristics and relationship patterns with environmental periodicity. The formation of scientific curiosity and investigative intelligence would necessarily focus on different phenomena without the obvious lunar laboratory that typically stimulates early scientific observation and hypothesis formation. Lunar phases provide natural experiments in celestial mechanics that often inspire early scientific thinking about cause and effect relationships, prediction accuracy, and the relationship between mathematical models and observable reality. Without lunar scientific inspiration, investigative intelligence might develop different approaches to understanding natural phenomena and scientific methodology. Toolmaking and technological intelligence would develop different relationships with temporal planning and cyclical manufacturing processes without the monthly timing frameworks that lunar cycles typically provide to complex project organization. The development of sophisticated technologies often requires temporal planning capabilities that coordinate multiple processes across intermediate timescales between daily work cycles and seasonal resource availability. The irony of moonless intelligence becomes apparent when considering that consciousness developing without lunar rhythmic frameworks might actually become more flexible and adaptable to environmental variation, but potentially less capable of the precise temporal coordination that typically characterizes highly organized technological civilizations. The absence of shared celestial timing references might favor individual cognitive flexibility over social coordination capabilities. Only the rapid pulse of abbreviated days and the slow drift of seasonal changes provide temporal structure for intelligence that must learn to organize its consciousness around purely terrestrial rhythms, forever more dependent on internal cognitive timing systems and less connected to the celestial rhythms that typically help synchronize complex thinking across social groups and coordinate the temporal frameworks that support advanced technological civilizations. In the deepest quietude of geological time, where change moves slower than thought, and stillness becomes a meditation spanning eons, the moonless world settles into its eternal rhythm, the rhythm of solitude, of waters that never learned to pulse with celestial heartbeats, of nights that never knew the comfort of borrowed light. Here, beneath skies empty of companions, the planet continues its ancient rotation, spinning through space with the same wild energy it possessed at birth, never slowing, never finding the gravitational embrace that might teach it patience. There, silence grows deeper now. Not the absence of sound, but the presence of a different kind of music. The song of a world that learned to make its own rhythms without cosmic guidance. In this quiet, the very stones seem to exhale with relief, settling into forms that will remain unchanged for millions of years. The oceans, too, find their rest, their stratified layers maintaining distinct identities like sleeping giants who need not wake to tidal alarms. And in this deepest quiet, where even the concept of monthly cycles fades into theoretical possibility, where tidal pools exist only as might-have-beens, where the night sky stretches empty of any nearby companion, there exists a peace that is both profound and lonely. The peace of a world that learned to exist entirely within itself, to find beauty in its own unguided spinning, to create life without the mixing rhythms that usually stir the cauldrons of evolution. The last light of this abbreviated day fades into darkness absolute, darkness unrelieved by any reflected radiance from above. In this darkness, the world rests, not in the gentle silver peace that moonlight usually brings, but in the complete, honest darkness of space itself, the darkness that teaches planets to be sufficient unto themselves, to find their music in the simple, persistent rhythm of rotation, to dream dreams illuminated only by starlight and their own quiet inner fire. Sleep well, moonless world. Sleep well in your solitude, in your silence, in your peace that knows no tidal disturbance, no lunar interruption of perfect planetary rest.